Welcome everybody again for this third day of the school. Today we're going to have three speakers, and the first one is Matteo Marsili, who is a professor researcher here at ICTP, who will give a tutorial on stochastic processes. So I'll leave the floor to Matteo. And before we start, just let me remind you a couple of rules. So if you have questions, you can either post them in the chat or you can raise the hand with the Zoom feature. And if you're following from YouTube, you can ask a question by posting the question on the YouTube chat, and I'll keep track of that. So please, Matteo, thanks for...
Okay, welcome everybody. So in this is a tutorial, and the idea of this tutorial is to give you an idea of how you introduce stochastic effects in theory and simulations of individual-based models. Okay, so going from the ordinary differential equations that you have seen in many of the talks to models that also include stochastic effects. Okay, so so the idea is, say, this is just an example of some data from epidemics. This is, I don't remember exactly what the epidemics was, but as you can see, the dynamics of the number of infected in time is not at all a smooth function as you would get from the integration of differential equations for populations. So which means that you have to include other terms. So one, of course, is seasonality. So a term that depends on time explicitly. But the other one is also what I shall call generally noise. And the idea of this lecture is to discuss what type of noise and how this noise comes about. Okay. And in particular, I'm going to discuss demographic noise. Okay, so if you take a simple model like an SI model, then these are the two differential equations that you have. And generally, if you integrate these two equations, you would get just a continuous curve. But if you are interested in a model that is going on in a real population, then the increase in the number of infected individuals has to be an integer. So if you look closely at this curve, it should be like a step function. And these steps corresponds to microscopic events where a particular individual in the population get infected. Okay, because he bumps is a susceptible individual, he bumps into a infected individual, and as a result, he becomes he or she becomes infected. Okay, so this is what we want to describe. So what we want to do is to modify these equations of this model in order to take into account this discreteness and these stochastic events. Okay, so let's start from the very simplest case. Let's look at just one individual, and let's imagine that he may get infected in time with a rate which is constant in time. So this probability RDT that a new individual will get infected in time interval from t to t plus dt. And these events are independent. Okay, so you can represent this on a on a line, and these events are represented by these star symbols. And if you plot the number of individuals as a function of time, then each time there is an event, the number of individuals will increase by 1. Okay, so how can one simulate this event? Imagine you want to write a computer code that generates this function I of t. Then one idea is to fix a small dt, and then for every interval with a probability r dt, you will increase I of t by 1. Okay, and you can do this for a particular interval t plus dt, and then you advance time to t plus dt. You consider the next time interval. Okay, and for each interval you should draw just a random number, and if this random number is less than r times dt, then you increase I by 1, otherwise you don't. Okay, so now how should you choose this dt? So the idea is that if you choose this dt too large, you may have that more than one individual gets infected in this time dt. So dt should be very, very small. But if dt is very, very small, then your simulation is going to be very small, very slow. Okay. So the question is, can we find a more, say, a smarter way to simulate these problems, simulate this process? And the idea is to ask, well, how much time, given that I have an event at time t, how much time should I wait for the next event? Okay, so this is a little bit of math. So essentially, if this P0 of t plus s is the probability that there is no event that occurs in the interval between t and t plus s, then because of time translation invariance, so this probability will only depend on s, will be constant in t. It will be the same for every interval. So, and this probability can be written as the probability that the time that you have to wait has to be larger than s. Okay, so it will be the integral from s to infinity of the PDF of the probability density of this waiting time. The next observation is that if you ask this question for two consecutive intervals of length S1 and S2, then it must be that the probability that you don't get infected in an interval of length S1 and S2 is the probability that you don't get infected in the first interval times the probability that you don't get infected in the second interval. Okay, and this should be true for whatever is the size of the intervals. So this requirement implies that this probability, which is a cumulative probability of this waiting time distribution, must be an exponential. Okay, must be e to the minus r times s. And then the PDF is just given by the derivative of this, and it's the PDF of the waiting time is just r e to the minus r times s. Okay, so now we have this probability distribution. It is very easy to draw a random variable which has this probability distribution. It's just given by this formula here, where rand is a uniform random variable. And so what you can do to simulate your process is just to draw a random variable TW with this PDF. Then increase your I of t by 1, and then advance time. And then you can repeat it in this way many times, okay? This is a more efficient way of simulating this process, because it requires you to draw fewer random numbers, and it's also exact, it's not approximate. Okay, so you can also do the same simulation more efficiently with a larger fixed dt. If you observe that the probability to get k events in an interval of length u is given by the Poisson distribution, okay? So, and so in this case, essentially you can keep dt fixed, draw the number of new infected from this distribution, and then advance time by u or by tau, essentially, okay? Okay, so all these mathematics that I've been describing is essentially what is called the Poisson process, and is a process that describes events that occur and that have no memory, because essentially in every interval you can have an event independently of whatever has happened before. Okay, so now let's go back to our problem, that is that of simulating a population model like the SI model. Now, what happens is this is a little bit more complicated, because now we have two populations, the susceptible individuals and the infected individuals. So there are two compartments in our model. So we can say that for every individual, there is a variable xi, which is either 0 if he's susceptible or 1 if he's infected. So and the model is, it's a model where at each time interval t plus dt, each susceptible can become infected with a certain rate, and each infected can become susceptible. So now what is the, however, the important point is the rate at which a susceptible individual becomes infected depends on how many infected individuals are there, how many susceptible individuals are there, and also on the state of the individual. Of course, in order to be infected, an individual has to be susceptible. In order to become susceptible, an individual has to be infected. So this rate generally depend on the variables xi. So this makes the simulation a little bit more complicated. But again, you have you can see this simulation as a situation where you have n Poisson process which interact with one another. Okay, and so let us see how we can deal with this situation. Okay, so imagine that we are at time t, and then each individual, which is represented by a different line here, is in a particular state xi, and at each time, every individual, each of these states can change. Okay, so now we can use the idea that we developed before, and we can draw waiting time from the exponential distribution and ask ourselves when is it that the state of Mr. I will change, okay? And then you can ask yourself, what is the individual that will change next? This will be the one for which the waiting time for the next event is the smallest. Okay, and then you can simulate this process by just finding who is the guy with the minimal waiting time. You draw waiting time for each of these persons. Then you find who is the guy with the minimal waiting time, and then you advanced, you change the state of Mr. I star, and you advance time. Okay, so this is exact. You need to draw n random variables, which are the waiting times for each of the individuals. But well, you can argue that when you perform when you change the state of Mr. I, you don't need to redraw the waiting times for the other people unless their state has changed. And this is because of the memoryless property of the Poisson process. Okay, so can we do this simulation even better? So the idea is that essentially we can figure out what is the time that we have to wait for the next event to occur, regardless of which is the variable that will change its state. So imagine that we are at time t, and where this violet guy changed the state. And then at this point, essentially, we are interested in understanding which is the next event that will take place. Then we don't need to keep the distinction between the different individuals. We can just deal with this as a single Poisson process. And we can just find what is the time that we will have to wait for the next event to occur in this combined Poisson process. Then once we find this time, we can also ask who is the guy, what is the probability that the guy that changed the state is a particular guy, I star. Okay, the way to do this is simple. Well, the probability that the minimal time that you have to wait is larger than t is the probability that all the times that you have to wait for the next events, the events on all individuals are all larger than t. And because of this, because these are independent events, then you can factorize this probability. Then you know that all these are exponentials. And then you can compute directly what is the probability that the next event will occur later than t. And this is e to the minus this capital RT, where capital R is just the sum of all the rates, of all the individual rates. So you can just draw an exponential distribution, an exponential random variable from using this simple formula, okay? Then the second step can be done easily because if you ask yourself, what is the probability that the next guy that will change his state is Mr. I, then this is the probability that his or her, his waiting time is smaller than all the other waiting times. And you can compute this because this is just the expected value on his waiting time that of the probability that all other waiting times are larger. And when you do this integral, you get a very simple answer, which is just the ratio of the rate of the process I divided by the capital R, which is the cumulative rate, or the rate for the whole population. Okay, so you see that if you you can do a simulation very efficiently in this way by just drawing the time for when the next event will occur, and then drawing which is the individual that will change his state from this probability distribution. And this way of simulating processes like this is called the Gillespie algorithm. So if you go back to the SI model, then here we are interested in two variables: the number of infected individuals, which is just the sum over I of all these random variable xi, and this is just, and the number of susceptible is just the total population minus I. So, and the rates are equal to beta times the probability that if I pick, if I meet a person at random, it will be infected. This is just I divided by n. And this is the rate for all the people who are susceptible, for which xi is equal to 0. And otherwise, the rate to recover is just mu. Okay, and this is the rate that applies to all individuals whose state is infected, so for which xi is equal to 1. So essentially the prescription that I told you before is that if you want to simulate the SI model at an individual level, you just draw a waiting time for the next event from an exponential distribution with this formula by drawing a random number, uniform random number, taking the log and divided by R. And where R here is given by this simple formula, it depends on I. And then you draw I star from the formula that I told you before. And this essentially corresponds to advancing time to TW by TW, and to setting the number of infected individual at time T plus TW as the number of infected individual at time T minus 1 with probability mu R divided by R. This is the probability that yes, that sorry, this I think there should be a plus here, and with probability, the probability that I get infected infection more should correspond to IT plus 1, and otherwise IT decreases by 1. Okay. So if you write a program, then this is essentially it's very easy to write a program, and then you can compare what is the difference between the ordinary differential equation, the usual ordinary differential equation, which is the black line, and the curve that you get from this stochastic simulation, which is the green one. And as you see, you get some stochastic fluctuations. Okay, so a couple of questions, a couple of comments, if you don't have questions. So one comment is why can't I use a finite dt and use the fact that this is a Poisson process, so I know how many events occur in a time dt in a Poisson process, because it's given by the Poisson distribution, as I told you. Well, the problem is that when an event occurs, this changes the rate of other events that can occur. Okay, so one cannot use a finite dt in this case. And so this way of simulating can also be written down, so can be described mathematically by what is called the master equation. And the master equation is an equation for the probability of having I individuals infected at time t. And the idea of this master equation is that essentially you want to understand, if you want to understand how this probability changes in time, then you have to consider what are the events that contribute to increasing this probability. And these are the events where either you have one less individual who is infected and then someone gets infected, and then you go from I-1 to I, or you get I+1 infected individuals and then you get one of them who recovers. Or otherwise, you have infected individuals and some of them either recovers or some other susceptible individual gets infected, so you go to I+1. And notice that here, these two terms that describe the transition from I to I+1, I to I-1, are proportional to the probability of having I individuals at time t, and they have a minus sign because the probability then decreases, okay? So now, of course, in a real situation like the one I told you before, there are other stochastic events. In particular, their rates themselves depends on time. And so you should also take this into account. However, typically, this does not change much the way in which we have been doing our simulation, simply because the rates, so the time, the typical time over which one event occurs is of order 1 over the total population, over the size of the total population. And you don't expect rates to change that much over such a short time interval. Okay, so essentially, this Gillespie algorithm can be used also in the case where there is seasonality. Now, there is an interesting observation that has been made by McCain and co-workers some time ago. And this has to do with the fact that you can get seasonality even without seasons. In the sense that if you look at this master equation, the solution of this master equation for systems stationary state with a fixed point and essentially whose deterministic evolution would be very smooth, then instead, if you look at a finite population size, the evolution of a finite population, you find these large stochastic oscillations, okay? And this is just an effect which is entirely due to the stochastic nature of the system. And this has also been applied to epidemics, as you can see in this plot, which is taken by from this paper where also Mercedes was involved. Okay, so I would pause here if there are questions, because then I'm going to change a little bit subject.
So I think,
let's see
yes,
how.
yes, you are exactly half an hour, so half of the time. So it's perfect. So I think it's a good moment to stop and see if there are questions from the audience. So if you have question, please use the raise hand or type it in the chat. Yes, please, Maud, unmute yourself and ask.
Hi, I just try to understand your slides, the previous slide, when you show about stochastic. Yeah, the previous one, this one. So meaning that here we can see that that slide picture. Yeah, that one.
This one.
Meaning that,
okay.
Meaning that here we can see the discrepancy between prediction of the deterministic model and stochastic model, is it? Because
yes.
Here we can see that the stochastic can predict like the solution with like some sort of periodic solution or cycle or something. But it seems like the deterministic part giving you stable steady state, right? That is what you are trying to say.
Exactly. Yes.
And the reason is because of the demographic stochasticity.
Exactly. Because you have this demographic stochasticity, you can have this oscillation. So this is a property that depends crucially on the Hessian of the when you compute the Hessian on the stationary state of the model. Okay, so but it's if you want to know more, I think it would be ideal if you go to these two references where the problem is discussed in detail. Okay. Hello?
Yes. I mean, yeah. Maud, is it okay? Okay.
Let's assume it is okay.
There is a question in the chat from Jordi, who asks, is the period of seasonality in the stochastic process the same as the period of the deterministic damping?
In this case here, I think I cannot, I don't recall exactly, so I would not like to make statements that are not exact. And but yeah, so this is essentially related. So indeed, if you see in these plots the damping, or if you look at the period of the deterministic dynamics, is pretty much synchronized with the period of the stochastic oscillations. So so in this sense, these two things are clearly related. And as I told you, well, if you look at the fixed point condition, then and you look at the Hessian, then this periodicity here of the deterministic dynamics will be related to that. And this is the periodicity which is explored by these stochastic fluctuations in a finite system.
Okay. There is another question by Solmas, who is asking, in the method of adding noise to the master equation, can we add noises with different distribution or different frequencies, like pink or white noise? how can we change this kind of parameters in Gillespie algorithm?
Okay, so so if you want to add so population noise is given by is a discrete noise and is given by this description that I gave you here. So if you want to add other type of noise, which is exogenous noise, then this can so like a stochastic forcing with a particular distribution. That of course can be done, but probably this is more relevant. So we can discuss this better in the next part of the lecture.
Okay. There is.
Oh, sorry.
Sabina, yes, if you want to ask a question, please go ahead.
Yeah, can I ask a question? I understand mathematically that there is an equation, as you said before, that we can find the process which occurs next. But what does it mean ecologically? Like how we can translate that in what is happening? Like the model can predict how the distribution is gonna go in the future for the next time. I'm sorry if I don't explain myself well.
No, yeah. So here, this is a model. Say the stochastic, the master equation. This is a model where you make a very simple assumption on the dynamics of what is going on. You say that this is a model where is a well-mixed population of infected and susceptible. They bump on each other, and you have these processes. And for this model, under this condition, you can compute in this way the probability distribution. If you are at time t, you can compute what will be the probability distribution at a later time. Okay. Now the question is how much this model describe a real ecological, real system ecology, and this is something on which you will learn across all the. I mean, I think this whole winter school is about that.
Okay.
Essentially.
Thank you.
I mean, the tutorial is just to give you a sense of if you look into this model, what is the mathematics and what is the what are the arguments that are on the basis of these models. Okay.
Yeah, thank you.
There is, if there is time, yes, there is another. I would say there is another question by Mod, so we can go ahead with that, and then you can continue.
Okay, thank you. I got another silly question for you about that picture, right? When you got this divergence between deterministic and stochastic prediction, it seems like the deterministic curve should be like of stable spiral path solution. Is it always the case? Can you get that whenever you got like the stable node case or something?
No, you don't get it. So, for example, if you, for example, for a simple SI model, as the one I described, you don't get this dynamics. You don't get this oscillation. So there are specific conditions on the rates, on this rate that make this phenomenon possible. Okay, and again, if you are interested in this, I really recommend you go through these very nice papers that discuss this property in detail.
Okay, thank you.
Okay.
Great, I think.
Okay. Let's go ahead. Okay, so now what I would like to discuss is probably a more direct way of introducing a stochastic effect into the dynamics of population dynamics by adding a term directly to the deterministic equations. Okay, so if you have an equation again for the SI model for the number of infected, so this would be the deterministic dynamics. So what you can ask is, what is the term that I should add to this model in order to account for population noise? Okay. So, so this is essentially a subject that goes under the name of stochastic differential equations. And the summary is, if you want, the two-line summary is that the effect of noise, you think about the effect of noise on a finite and small time window, is the accumulation of many infinitesimally small events. So essentially the noise that you should consider can be considered as the sum of many random variables. So it is essentially described by the central limit theorem. And because of this, the noise, the type of noise that you should add to this stochastic differential equation cannot be anything, but it has a very specific mathematical form, which is essentially related to what is called the Wiener process, okay? And the main thing that you should remember about this Wiener process, that I call W here, is that it's differential. So the increment in this stochastic function over a small time interval dt is of the order square root dt, okay? And this has very important consequences that really are important to take into account when you want to simulate this process, okay? So let me go through this in some detail, okay? So, as I told you, what we want to do is to take a differential equation and add noise to it, okay? In this case, I'm using this variable y, which is the fraction of infected individual in a population. Okay, so in order to give a meaning to this noise, essentially we should tell, how do I integrate this stochastic differential equation? So how do I get the value of the random variable y from at time t, from the variable at time t0, when I integrate this stochastic differential equation from t0 to t, okay? So the first part is rather easy because this is just a normal integral. But what is this integral of the noise? Okay. So now, in order to describe this integral of the noise, you should really think about it as what you would get if you discretize the time interval between t0 and t into small intervals of size dt. Okay, so the number of intervals is of order t minus dt, t minus t0 divided by dt, and this sum is the sum on the contribution of this noise over this small interval between of size dt. Okay, so now let's think about what should be the properties of this random variable xi, which is the integral of the noise over a small time interval of size dt. Okay, so first of all, if if we think these are, say, stochastic effects, then it's natural or reasonable to think that these are also independent and identically distributed, because noise is expected to represent something of which we don't know anything. And so if this is so, then the sum of these small effects is going to be to obey the central limit theorem. And so we know that this sum is going to be n times, where n is the number of intervals, times the expected value of this xi, plus square root n times the variance times Gaussian variable, okay, where the PDF of this variable z is a Gaussian. Okay, so in our case, I remind you that n, the number of intervals, or the number of variables that we are summing here, it's inversely proportional to dt. And also the expected value of these increments, because this is noise, is going to be 0. Okay, so now if you look at this term here, and if you want a finite limit when dt goes to 0 and n goes to infinity, then you should have that the variance of this random variable xi divided by dt should be finite. Okay, because otherwise you don't get a finite limit. Okay, sorry. So then. So this is what essentially defines the Wiener process. And the idea is that each of these xi, which is the integral of the noise over a small time interval dt, that I call dw, should be proportional to the square root of dt times a Gaussian variable z. Okay. And so I know that if I integrate this noise over a time from t0 to t, then I get a sum which will be of the order of square root t minus t0 times a Gaussian variable z. Okay. Okay, so this is the first lesson, so that this dw should be proportional to square root dt. And this tells you that when you do a program and simulate this Wiener process, then when you advance time, you should rescale things by square root dt. Okay, or your increments should always be of square root dt. So notice here that this defines a curve, which is essentially this Wiener process, which has a well-defined limit when dt goes to 0. And this you can see graphically by the fact that I have been running this program with two values of dt, which is 10 to the minus 3 and 10 to the minus 4, from time equals 0 to 1. And this is the function w of t that I've that I obtained. And you can see that, well, you cannot tell which is which. Actually, I don't even remember which is which. Okay, which one was integrated with the dt, which is 10 to the minus 3, and which one was integrated with the dt, which is 10 to the minus 4. Okay. Okay, so so the Wiener process, which is this stochastic random curve, is a very interesting object, mathematical object, and it has this process properties that you can show that it is continuous. It's a continuous path, and almost surely. And also it has independent increments. If you look at what is the increment of the Wiener process in a time interval and in another time interval that are not overlapping, then these are independent. And also, as I told you, the most important thing that you have to remember is that the differential of this Wiener process is proportional to square root dt. And because of this, this is nowhere differentiable. Okay, so we get some creative addition to the slides. So, okay, so now let's go back to stochastic differential equations. So what we have understood is that if we have a deterministic equation, which is the first part, dy is equal to a times dt, then the noise that we should add is proportional to this Wiener process, or to the differential of this Wiener process. Well, b can be any function that also may depend on y. Okay. So now, if I want to define what is the solution of this equation, then I should tell you how you integrate it. Okay. So, so in order to do this, you have two parts. One is just a usual integral, is a Lebesgue integral that you compute with the usual rules, like trapezoid rule or whatever you like. But the other one is stochastic integral. It's an integral that also involves dw, okay? And so you can think, well, okay, I will compute this integral in the same way. So define a time tau I, discretize in many, many small intervals. Define a time tau I between inside each of these intervals, and just evaluate this function at these points, and then sum this function times dw, and then that's it. Okay. However, if you think a little bit more closely, then what you find out is that the value of this integral depends on how you choose the midpoint. Okay, how you choose this tau I. In particular, what you can see is that if you look at this particular integral, which is w dw between t0 and t, then you can define it as the limit as n goes to infinity of this discretized sum. And if you take this tau I to be alpha times the endpoint plus 1 minus alpha times the beginning of the interval, then you get that the result actually depends on how you choose the midpoint. Okay, so it depends on this alpha. Okay, so then in order to give a precise meaning to these integrals, you have to specify how you choose this alpha, how you do this, how you compute the integrals, okay, how you integrate differential equations, okay, and this is called a prescription, okay, and the most natural prescription is just to take alpha equal to 0, which corresponds to what you do when you do forward integration of stochastic of differential equations. Okay, so so the consequence of this is that if you look at the differential, so the rules that this that these mathematics for integrals and differentiation obey are a little bit strange, because, for example, if you compute this integral here, you get one part which is what you would get if you just integrate if w were a normal function, which is just this part here. But also you get a new part, a new term here, which just comes from this this prescription and the fact that w is a stochastic function. More precisely, it comes from the fact that dw is proportional to square root dt. Okay, so when you compute the differential of a function of w, then this does not only contain, so this differential should be f of w plus dw minus f of w. So this does not, you have to expand f of w plus dw to second order term, not to only first order term, because dw square is equal to dt. And then you get also this term here, okay? So this is consequences for how you deal with stochastic differential equations and how you change variables. And because when you change variable, you have to always take into account that dw square is equal to dt. And so there is another deterministic term that comes out in your differential equation as a consequence of the stochastic term. Okay, so you can do many exercises, but let me go back to the SIS model. And so what this tells you, so for the SIS model, you can derive a stochastic differential equation, which is which has this deterministic part. And then the stochastic part, the fact that you have this stochastic part can be derived from looking at what should be the variance of the noise that you add here, okay? And the variance of the noise for each interval, you can see it as this form, and depends on dt. So here you should put the square root of the variance of this term here, which is given by this object here. Okay, then essentially you can run a simulation, just integrating forward this stochastic differential equation. And again, what you get is a path that approximates the deterministic solution, but it has this population noise added to it. Okay, and now how you can relate these two things that I've been telling you about population noise, the Poisson process and master equation, and the stochastic differential equation. Well, there is one way of doing this, which is rather natural, and it's called the Van Kampen system size expansion. I don't think we have time to go through it, but essentially what I want to tell you is that just these two different, what I've been telling you are not two different ways of, two different stochastic processes. It's the same stochastic processes discussed in two different ways, okay? Okay, so here are a couple of references to which are rather accessible for with a minimal mathematical say education. So, and where you can find all the things that I've been telling you. Okay, thank you very much.
Yes, thank you a lot, Matteo, for the very nice tutorial. So I think we have time for a few questions. So there was one in the chat that I can start to ask by Prajwal. I think you sort of answered that already. How does the stochastic prescription affect simulation? Does it even affect simulations?
It does. It does. So if you, because say, just to make you, give you some intuition. Okay, so when, so, okay, so sorry, let me go back to this point here. Okay, so let's take this example here, okay? So you see, when you take the expected value of this integral here, So if dw, if tau I is computed at the beginning of the interval, then dw and w are independent. If you take the expected value of this, this is going to be 0. Is this clear? If instead you take a midpoint, which is not the starting, not the beginning of the interval, you don't take ti as the tau I equal to ti minus 1, sorry, which is alpha equal to 0. Then if you don't take the starting point of the interval, then these two variables here, w and dw, are not independent. And so when you take the expected value, this is not going to be 0. So when you integrate, and so this means that when you integrate these stochastic differential equations, so you know, when you have an integration, when you have a normal differential equation, you can choose any midpoint you want. Okay, you can have say implicit methods where you essentially solve this where essentially here you estimate your function x of t at the end of the interval, so this becomes an implicit equation, etc., etc. So, and for normal differential equation, this makes no difference. Okay, it only changes the accuracy. It can only affect the accuracy with which you can integrate this equation. I mean, but if you have stochastic differential equation instead, you should be very careful how you choose the midpoint, how you integrate this this equation. So the idea of the Ito prescription is that the noise is at time t is independent of x at time t. Okay, is an effect which is is independent of whatever. Is this clear?
Yes, that part is clear. But my question more was along how does it show in simulation? How does this prescription show up in simulations? Like,
it shows in this way. So, say for example, if you so when you have a stochastic differential equation like this one, if you take alpha equal to 0 and you integrate it, you would get you would get a contribution which is like this one. Say for example, if you take alpha equal to 1/2, alpha equal to 1/2 correspond to a difference prescription which is called Stratonovich. Okay, then this other prescription is such that you don't have this other term here. Okay, you don't have this second term here. Okay, and so the rule that you apply to stochastic differential equations are the same as the rule that apply to differential equations. Okay, but and so the results are completely different. Also, if you do numerical simulations, the results well, not completely, but they are different. Okay.
okay.
So this is definitely something you should care about. You should be always specific about what prescription you are using when you are dealing with a stochastic differential equation. And I tell you this because also in papers that you can read, this is not always specified. Okay. But if you want your result to be reproducible, you should say what is the prescription that you are using in a stochastic differential equation.
Great. So there are a couple of more questions in the chat. So I think we have 5 minutes more to leave like a few minutes for a break. So next question from Zored. Can we study bifurcation in a stochastic model?
Yes, of course. So now bifurcation. So you always think of. So if you think at a say discrete map, then this is like I don't know Henon map or the logistic map. Then you can add noise in different ways. But then if you look at like something like Lorentz system, where you have stochastic, where you have differential equations, coupled differential equations, then you can also add stochastic noise to that, and see. And I think there are many people that have studied these problems. Yes.
Great. There is another question about multiplicative noise by Gianluca, who asks, are there models for which the stochastic differential equation involve a noise term that depends on the state of the system at that time? Say dW depends on X at time t.
Yes. So typically, you do this by saying that well, dW is always an independent increment, at least in the Ito prescription. So dW is always the differential of the Wiener process. What depends on X at time t is the variance of the noise, is B of X and of xt. Okay, so so this is the way in which you can build this dependence of X and T of the noise term on the state of the system.
Okay. Great. So, is there any other question?
I have a question.
Yes, please.
You mentioned that if the paper does not say what alpha they used, it's not reproducible. But then I was wondering if I can reverse engineer, and given a solution or some characteristics of the solution, I can find what alpha or make a or maybe a distribution of probability of alphas they used.
Yeah, so let's say, yes, you can, in many cases, infer what is the prescription that is being used, also because different communities typically use different prescriptions. So, say in theoretical physics, many people use Stratonovich prescription, and whereas, for example, in I think in epidemiology, the natural prescription is more the Ito prescription. But yes, I mean, it should be possible to figure out what is the prescription used. But I mean, when you write a paper, you should ensure that your results are reproducible. So you should state what is the prescription, essentially. It's on, yeah, it's on the it's on the side of the authors to specify this.
Great. So I think it's time to take a short break before the next tutorial. So thanks a lot, Matteo, again for this very nice introduction. And this is all this introduction is available on YouTube. So again, you can go back and rewatch this lecture, this tutorial as many times as you want. So thank you very much. So now we're going to take this small break, and we're going to be divided in breakout rooms as usual, and we'll be back in 4 minutes. So take this opportunity to chat with others or stretch your legs, get a coffee, etc. Great. So we will start in about 1 minute. In the meanwhile, if you're watching the school on YouTube, I remind you that if you want to ask question, you can use the chat of YouTube, and I'll read the question you asked to the speaker. So we are waiting for people to come back from the breakout rooms, and then we can start with the next tutorial. Okay, great. So I think that everybody is back to the main room. So it's my pleasure to introduce Zach Miller, who is a PhD student in ecology and evolution at the University of Chicago. So it's very early for him. It's like about 7 a.m. So I want to thank him for being with us so early, and he will give a tutorial on linear algebra. So please, Zach, if you want to share the presentation and unmute, great.
Let's see here. All right,
Great.
everyone see that?
Thanks.
Okay, well, thank you, Jacopo, for the introduction and the invitation. So the aim of this hour-long tutorial is to give a very brief survey in linear algebra. It's a field that has a lot of sort of terminology and kind of foundational baggage, and so the idea here is that we're not going to be able to go through too many proofs today. We're not going to be able to go through too many computations, but hopefully to kind of go through the important concepts to be able to use some of these ideas in the biological context. I'm going to sort of start with the real foundations, and we're going to sort of work our way up to some more kind of complex calculations and sort of ideas. So, the beginning might be review for many people, but bear with me, and hopefully we'll get to interesting stuff for everyone. And linear algebra, I think I'll make my little pitch, is definitely the kind of material, it shows up everywhere, and it shows up in so many different sort of guises that it's really worth seeing it repeatedly, thinking about it in different ways. So hopefully maybe this will be an opportunity to also get a sort of new perspective if it's content you've seen before. So any sort of introduction to linear algebra starts with the idea of a vector. So for our purposes, a vector is an ordered list of numbers. So I've shown a few here. And just a note on notation, often vectors are denoted either with lowercase bold-faced letters or sometimes with lowercase letters with a little arrow on top. I'm going to stick to bold-faced letters, but I'm showing both here just because you might see it. You might see them written different ways. So we think about vectors as a sort of ordered list of numbers. Our vectors will have real or complex numbers as their components. So these sort of constituent numbers, the entries in the vectors, are what we call components of the vector. And we'll, for the most part, be talking about vectors with real components, but sometimes complex components. And we can also think about vectors graphically, right? So this is the first kind of, already we're seeing that there's two ways to look at them. We can think about them sort of as these ordered lists, or we can think about them as a kind of arrow in space with a direction and a magnitude. So I'll go back 1 second. So this U here corresponds to this vector here, 3, 2. You can see that it's 3 in the first coordinate and 2 units up in the second coordinate. Similarly, the second vector, V, is this -1, 1. Okay, so this is the kind of geometric picture that we've probably all seen before. And then we can do operations with our vectors. So vectors of the same size can be added component-wise. So for example, if we want to take that vector u and v and take their sum, we add them, just add the components. So 3 plus -1 becomes 2, 2 plus 1 becomes 3. So the sum of our u plus v becomes a new vector 2, 3 that can also sort of live in the same geometric space. Graphically, we think about this as adding the vectors tip to tail, as people like to say. So we take the first vector u, and then at its tip, we place the tail of the second vector, and we get the sum uv. This vector addition, because it basically comes from the addition of the scalar components, the real or complex values in here. The addition follows all the normal rules of the addition of those numbers, right? So, namely, it's commutative, distributive, associative. So we can reverse the order of the sum here, and we get the same vector out. So vectors can also be multiplied by scalars, right? So we can take just a regular old real number here and multiply it by the vector u. And what that does is it just multiplies each component of the vector u by that scalar. So here our u goes from being 3, 2 to 3 halves 1. And in the picture here, you can see that we're basically scaling its length. So when we multiply by a scalar, we're stretching the vector, but not changing its direction in space. The only sort of exception when I say not changing the direction is we can sort of flip the vector by multiplying by a negative number, right? So now we're just taking the vector and it's remaining in the same sort of line in space, but the orientation is pointing the other way. So this is just the case of -1/2 times u. So combining these two operations, right, the component-wise addition of vectors of the same size and multiplication by scalars gives us a slightly more general notion of a linear combination. And this is a really foundational concept in linear algebra. So over here on the right, I'm showing that if we take any two vectors u and v from some set of vectors that we're going to call a vector space and some scalars c1 and c2, then we can write very generally the linear combination c1 times u plus c2 times v. And you can see here the sort of component-wise definition of this. So the outcome will always be a new vector w that's also going to be in our vector space, right? So we can say that the vector space is closed under linear combination. So it's the set of all vectors that we can get by making linear combinations of the vectors we start with. Okay, so let's talk a little bit more about linear combinations. So again, linear combinations generate new vectors from old. Given a collection of vectors, so you give me some vectors, the set of all other vectors that I can express as linear combinations of those is called the span. So this is another important sort of idea that we're going to rely on a lot throughout this tutorial. So just to kind of get a sense, I mean, to get a feel for using this term, here we say that w is in the span of u and v, right? So if I start with these two vectors u and v, I can produce a new vector w by taking a sort of a linear combination of u and v, a sort of weighted sum of u and v. And what that sort of looks like is again, I start with my u and v. Now I multiply them both by scalars. So I stretch v a little bit, I shrink u a little bit, and then I take these new scaled vectors and I sum them and I can produce w, okay? So because w is expressible as a linear combination of u and v, it's said to be in the span of u and v. So t is another example of a vector in the span of u and v, just to make clear that you know, we can use negative numbers to make these vectors point in the other direction. So v, I mean, this t is again just produced by scaling and then summing u and v. And we can also sort of strangely use span as a verb as well as a noun. So we often sometimes say things like u and v span the entire plane. So I'll kind of, skip to the punchline here and say that I show you w and t, but really we can produce any vector that we want that can be drawn in this plane by taking combinations of u and v. And so this leads us to another really important idea, which is this idea of linear independence. So if we take a set of vectors S, and none of the vectors in that set can be written as a linear combination of the others, then we say that S is linearly independent. If that's not the case, then S is linearly dependent. So if there is a vector, or in that case, there might be many vectors in S that can be written as a linear combination of other vectors in S, then the set is linearly dependent. So a few more examples. So in this picture, if we consider the set just of u and v, this set of those two vectors is linearly independent, okay? And that's because if we take just v on its own, the only way to sort of take linear combinations of v by itself are just to scale it. So all we could do is sort of shrink or stretch this v. We can never produce u by doing that, and vice versa. The set u and w is linearly independent for the same reason. But the set u-v-w is linearly dependent now. And that's because, as we just saw, we can produce w as a linear combination of v and u, okay? So we're going to see this idea again of linear independence again and again. And linear independence leads right away to another concept. That's the concept of a basis. So a linearly independent set of vectors that spans a vector space. So we specify some vector space, for example, a plane here. And if we have a set of vectors that spans it, so they can generate, through their linear combinations, they can generate any other vector in the plane. And they're linearly independent, then they form a basis for that space. Okay, and the idea of a basis is sort of an idea of a kind of minimally sufficient set of vectors, right? So the spanning part tells us that these vectors are enough to generate the entire space under consideration. The linear independence part tells us that none of them are redundant. So if we add more vectors and this set becomes linearly dependent, that means basically we have more vectors than we need to span that space. So as some examples here, the set UV is a basis for the plane for R2. So I use this kind of fancy R, right, to denote the real numbers, and the 2 to say basically the plane, the set of pairs of real numbers. UW is also a basis for R2. UVW is not a basis for R2. And the reason is because UVW, while it does span R2, so we can use that set to generate any vectors in R2, it's a linearly dependent set, right? So it's not minimal. It's sort of has redundant vectors in it. And U is clearly not a basis for R2 because, of course, U can only generate, we can only use U to generate vectors that lie sort of on this line in the direction of U. So we can't generate any vector in the plane. So the idea of a basis is actually one that is, I think, in many ways kind of familiar. So even if you haven't really looked at linear algebra in this sort of formal way before, anytime we sort of work in a coordinate system, we are usually thinking about a basis called the standard basis. So even the kind of axes that we often draw for like a 2D or a 3D space, we can think of as basis vectors. So this is the standard basis. It's often convenient to work sort of in reference to the standard basis. So here we often use E I to denote the ith standard basis. So E1 is the vector with just a 1 in the first component and zeros everywhere else. E2 is the vector with a 1 in the second component and zeros everywhere else, and so on, for whatever kind of space that we might want to look at. And so in this picture, right, these are just vectors of length 1 in the direction of the usual sort of coordinate axes. And then when we write, for example, whenever we do sort of Euclidean plotting, right, we think about kind of ordered pairs of numbers like A, B, and we can think about these just as linear combinations of the standard basis vectors, right? So a scalar A times E1 plus a scalar B times this vector E2. And then that just looks like, in component form, looks kind of like this, A0 plus 0B. So all this is to say is that these concepts are ones that we actually kind of work with all the time. Okay, so far we've relied a lot on the 2D picture. The real beauty of linear algebra in a lot of ways, and one of the reasons, I mean, the sort of primary reason it was developed is to kind of deal with a common notation and a common set of tools to deal with very high dimensional spaces. So spaces of sort of arbitrary dimensions. So, you know, in physics, we might think about the space of sort of physical coordinates, like, you know, 3D space or something. In biology, we might think about our space, our vectors as being maybe the abundance of different species in a community, right? And so if we go to a diverse community, we might have hundreds or thousands of species. And so we might be dealing with sort of vectors that represent the state of the community that have hundreds or thousands of components. We might think about the concentration of molecules in a cell, whatever. The kind of nice thing about linear algebra is the tools we're going to develop can accommodate, you know, anything from 1 to 2 to 3 to 10 to 100 to 1,000 sort of components at a time. So while it's useful to draw the 2D pictures, and I'm really not much good at drawing anything beyond the 2D picture, it's useful to right away start thinking about dimensions beyond, or sort of other than the two-dimensional picture. So let's take a moment and think about now the three-dimensional picture, right? So we have the vectors S and T. Do these form a basis for the space R3, so for the three-dimensional space? It turns out no. So as a kind of counterexample here is a vector. You can try as hard as you'd like. You can never write this vector as a linear combination of the other two here. Now, I sort of just pulled that vector out of thin air, and we'll see as we go along kind of how we address this question more systematically. But this is to say that in the space R3, two basis vectors is not going to cut it to span that space. But we shouldn't say that S and T are not a basis generally. So they're not a basis for R3, but they are a basis for some space. And they're a basis for what we can call a subspace of R3. So sort of geometrically, they form a basis for a plane, a two-dimensional space that we can think of as kind of embedded in R3 that goes through the origin of the three-dimensional space, but it is a kind of lower dimensional space within it. So that's a perfectly good sort of vector space in its own right? It's closed under your linear combinations. So if I take linear combinations of S and T, I'm going to produce new vectors that are in that subspace. But these two vectors don't span the entire R3 space. And so I may have already slipped and used this word because it's really hard to avoid it. But this leads us to the important concept of dimension. So we're used to thinking about dimension kind of heuristically. And linear algebra gives us a very kind of nice and precise way to think about the dimension. So if we have a vector space, it's defined by a basis. So there might be multiple, there are in general many choices of a basis that define some vector space, but given a basis, we've specified a vector space. That the size of that basis gives the dimension of the vector space. Okay, and the sort of way we've defined a basis, so this fact that the basis has to both span the space and be linearly independent, these two kind of conflicting requirements, right? So one is this like requirement that the set of vectors are sufficient to span the space, and the other is that they're kind of minimal. These two requirements mean that the dimension is a unique number, right? So any basis for the same vector space will have the same number of elements, and so the same dimension. Okay, so I've shown you that we can take two vectors and combine them to produce a new vector, as a linear combination. But how do we kind of go backwards? So if I have some arbitrary vector and I have some basis, how do I represent that vector as a linear combination of the basis vectors, right? So how do I kind of write it in the space defined by that basis? So this problem, while it seems kind of like a sort of intellectual exercise, it's equivalent to solving a system of linear equations, which is really one of the most important tasks that we have in science. So linear systems of linear equations show up just about everywhere. They are historically extremely important and really motivated the development of linear algebra. And so let's kind of see quickly that these two exercises are really the same. So here the graphical picture is that we have some v and u, we have some w, and I want to find what are these two scalar coefficients c1 and c2, such that I can write w as a linear combination of u and v. Okay, now let's look at something that at first glance is totally different, right? So here's a system of linear equations. So this kind of problem arises all over the place. And we have here three unknowns, x, y, and z, and then we have coefficients for each of those unknowns. And then on the right-hand side of the equation, we have these just like scalars. So what we can sort of see if we write down the system in this kind of nicely formatted way is that these coefficients 2, 4, and 7 all get multiplied by x. These coefficients 1, 4, and 2 all get, or -2, all get multiplied by y. These coefficients -1, 2, and -3 all get multiplied by z. What that kind of suggests is that this kind of ratio 2, 4, and 7 are fixed, right? So by kind of changing values of x, we can sort of only change these values sort of in lockstep with each other. And we can sort of see that we can actually rewrite this equation with this 2, 4, 7 now as a vector, and this x as a scalar coefficient out front. So we can really recognize this system of linear equations as exactly the sort of linear combination problem we were talking about, right? So now here we have some vectors, 2, 4, 7, 1, 4, -2, -1, 2, and -3. And we want to find a linear combination of them such that we produce this kind of target vector, or this like arbitrary vector, -1, 4, 3. And so we want to know what are these coefficients x, y, and z. And to do that, we need to introduce the idea of a matrix and develop a little bit of machinery here. But first, maybe if anybody has any questions at this point, before we keep going, feel free to raise your hand.
Yes, so I think it's a good moment to ask question. If anyone wants to ask one either in the chat or raising the hand, I think we can take a couple of minutes to summarize. Any question? No, I think it's the sign that everything is extremely clear.
All right, great.
Thanks.
Then we'll just
Go
keep
ahead.
moving. Okay, so we're going to pause on that question for just a second to introduce this kind of new machinery. So now we're looking at matrices. So a matrix is just a rectangular array of numbers. So before we were looking at vectors, which were sort of just a list of numbers. Now we're just looking at kind of a structured array of numbers. So the notation we're going to use consistently is that a matrix is denoted just by a capital letter, so like A, B, or C. You can see here matrices can kind of have different sizes. So that's kind of the first important thing to talk about. the size of a matrix is given by the number of its rows. So each of these kind of like things across here we call a row, and the number of columns. So each sort of like of these stacks of numbers here is just a column, and the kind of usual format that we give for the size of a matrix is like rows by columns. So this matrix down here, A, for example, is 2 by 2. This one in the middle is 3 by 3, and this one on the right is 3 by 2s. Okay, so the rows and columns don't necessarily need to agree with each other. When we talk about matrices, we usually talk about elements. Why we use elements for matrices and components for vectors, don't ask me. But the elements of a matrix are these numbers that make it up, right? So here we can talk in general about like an n by m matrix, so a matrix with n rows and m columns, and its entries are denoted by a little a ij, so I telling us which row, so a number between 1 and n, and j telling us which column, a number between 1 and m. So for example, this 1 here is in the first row of b and the second column, so we would call that like b12. This 10.5 here is in the second row and second column of C, so we might call that C22. Okay, so like as with vectors, we can sort of operate on matrices. We can add matrices of the same side element-wise. So this is much like the addition of vectors, right? We add these two matrices. We take 2 plus -1. We get 1 in the sort of 2 in the 1, 1 position. In the 1, 2 position, we add 3 and -3. We get 0, and so on. Matrices can also be multiplied by scalars. So as before, we multiply by a scalar, and that means that every element of the matrix is multiplied by that scalar. So this -2 just goes sort of inside the matrix to each entry, and you can follow the multiplication there. So again, these I think lectures are going to be available later. So if I fly through any of these examples, you can always go back and take another look. And a note that, so again, we have the sort of notion of a linear combination here. So linear combinations of matrices, as with vectors, produce new matrices. And what that actually tells us is that really matrices form their own vector space. So we can take any two matrices at the same side, produce linear combinations, we get a new matrix of the same size out. Okay, matrices come with two new and slightly more interesting operations, transposition and multiplication. So the transpose operation, which we write with this little t here, sometimes confusingly because it looks like a power, but this t is really a special operation that takes an n by m matrix and just basically flips it on its axis. So the outcome of this transposition is an m by n matrix, where now the ij entry of our new resulting matrix was the ji entry of the A matrix. Okay, so here's an example. If we take this matrix A and we take its transpose, now we just sort of flip it, and what was the sort of 2-1 entry, the A21, becomes now the 1-2 entry. So that's where this 2.2 goes from here to there. So that's fairly straightforward. Matrix multiplication is worth talking about for a minute longer. So we can multiply matrices, but the sort of multiplication operation is somewhat different than how we extend addition. So whereas addition of matrices works element-wise, multiplication of matrices is kind of a new thing altogether. So if we take two matrices, A, which is n by m, and B, which is p by q, we can multiply these two matrices only if the number of columns of A, so this m, is equal to the number of rows of B, this p here. Okay, and we'll see why that in a second. So in this definition, for matrix multiplication, the product of these two, A, B, each of its entries, so the the ijth entry, for example, down here, is defined by taking the sum of many products over the entries of A and B. So we take, again, to get the ijth element of the AB, we take the AI1 plus B1J plus AI2 plus B2J, and so on. So there's kind of in compact summation form, we sum basically over all of the columns of A and all of the rows of B. So that's this K, this index of summation, for whatever I and J we're interested in. Okay, so here's that in action very, very briefly. So to get the product of these two matrices, let's first think about the first element of the product, right? So the 1, 1 element, which here is a 4, we get that by multiplying basically the first row of the first matrix by the first column of the second matrix. So we have this 2 times -1 plus 3 times 2. That should give us -2 plus 6, which is 4. Okay. We can try to do this for any of the elements of the resulting matrix. So I'll just go through one more. So this 5 down here, which is in the second row in the first column, we get by multiplying the second row of the first factor matrix and the first column of the second factor matrix. So we get a -1 times -1 plus a 2 times 2, and that gives us 5. So it's worth spending a little time practicing this if it's not something you're familiar with. I'll leave the formula up here for a moment longer. Okay, so matrix multiplication, it, again, works a little bit differently than normal multiplication. And one thing right away that's a bit different is now the multiplicative identity. So the element such that if we take B times the multiplicative identity, we get B back. So in normal multiplication, that's just played by the 1, the number 1, right? So if we take 10 times 1, we get 1 back. In matrix multiplication, that identity element is what's called the identity matrix, and it's a matrix, a special matrix that looks like this. So it's an n by n matrix that has 1s on the diagonal and 0 everywhere else. And so it's worth kind of trying it out for yourself. But if you multiply any matrix by this in, you'll get just the original matrix back. Okay, it's worth noting that this identity matrix is a very special example of a kind of more general type of matrix called a diagonal matrix. So it's a matrix that only has non-zero elements on its diagonal. So for the elements like AII, A11, A22, only when the I and the J equal each other. And we'll see some more diagonal matrices soon. And another note, another sort of important fact about matrix multiplication is that it's associative. So if we have A times B times C, we can multiply A and B first, or we can multiply B and C first. It doesn't matter. And it's distributive. So if we have A times the sum of two matrices, we can distribute that multiplication across the sum. But it is generally not commutative. So A times B is not equal to B times A. And this is maybe made, maybe you might have already sort of seen that this kind of has to be true because of the way we define matrix multiplication, right? So it depends on the sort of interior dimensions, this M and P being the same. So if we take now B times A, then we have to worry about whether Q and N are the same, these sizes. So that's just to say that A times B will not generally be the same as B times A, even when the sizes work out, actually. Okay, so matrix multiplication, we can actually now go back to our vectors for one moment. And matrix multiplication kind of gives us some interesting concepts when we look at vectors. So first, if we take the transpose operation, we turn our usual vectors. So I've been writing vectors as columns, and that's just conventionally how we think of them, as sort of vectors are almost like matrices that have n rows and one column. But if we take the transpose of a column vector like that, we get a row vector, which is now kind of like a 1 by n matrix. And if we take two vectors and we apply the transpose to one of them, now we can actually multiply them using matrix multiplication. So for example, if we take a vector v and a vector u that are the same, that have the same number of components, and we transpose the v, then we have a 1 by n vector times an n by 1 vector, okay? Or essentially a 1 by n matrix times an n by 1 matrix. And so we can just multiply them using the usual matrix multiplication rule. This is often called the dot product, or it's an example of an inner product. And you can see down here, we just end up with v1 times u1 plus v2 times u2, and so on. And this is a really sort of important operation that will come up all the time. One very interesting connection here worth seeing is that the inner product or dot product of a vector with itself, so v transpose v, is equal to the Euclidean length or the norm of the vector squared. So if we take v transpose v, we have v1 squared plus v2 squared plus v3 squared. That should be a squared, sorry, here. And then if we were to take the square root of this, we would get the normal sort of Euclidean length of the vector. And if we take the inner product of two different vectors, or even the same, the product is actually going to be a function of their lengths and their angles. So we can explicitly sort of write it as a function of their lengths and angle. So v transpose u is going to be equal to u transpose v. So this operation is symmetric in this case. And this will be equal to basically the length of u times the length of v. So the square root of the inner product u transpose u, the square root of the inner product v transpose v, times the cosine of their angle. So in this picture here, right, this inner product that comes out is just a function of basically the length of u, the length of v, and then this angle here formed by the two vectors in space, which holds even in the kind of higher dimensional picture. And importantly, if v transpose u is equal to 0, so if this inner product is equal to 0, that can only happen for non-zero length vectors when this cosine term is equal to 0. Okay, and so what that means is that the angle between these two vectors is basically a 90-degree angle, so that it's a right angle. So this idea of orthogonality generalizes the kind of idea of being perpendicular or at right angles that you've probably seen in a geometry class. Okay, so that's just a little aside. Now back to matrix multiplication. It's often useful to view matrices as sort of bundles of column vectors. And now let's just think about multiplying a matrix by a column vector, right? So we have a matrix sort of arbitrary size, and we're going to multiply it by a column vector, an m by 1 matrix, essentially. If we kind of think through the matrix multiplication, what we see here is that this v1 is going to multiply all of the elements in the first column of A. The v2 is going to multiply all the elements in the second column. The v3 is going to multiply all the elements in the third column. And so we can actually sort of rewrite this matrix multiplication as v1 times this sort of vector now formed from the first column of A, v2 times this column vector formed from the second column of A, and so on. So really taking this product A times V is giving us a linear combination of the columns of A. Okay, so this is bringing it all back to sort of the question we had, maybe 20 minutes ago now, about sort of representing a vector in a basis, or equivalently solving a general linear system. So these two things are both equivalent to the matrix equation AV equals B. So we have a matrix A, the columns of which are our basis vectors. We have a V, which is a vector of unknown coefficients that we'd like to figure out. And we have a B, which is kind of an arbitrary target vector. So if this were a sort of normal equation in scalars, right, if this were just like 4 times V equals 2, the way we would solve it is we would multiply each side by 1/4, right, by 1 over whatever this coefficient is. So because we're dealing with matrices, we can't quite do that, but we sort of want to find a new matrix, an inverse matrix for A, such that when we multiply this inverse A times A, we just get V on the left. So very much sort of in analogy to what we would do solving just a normal kind of linear equation. So here, what I'm writing is that this A inverse times A gives us the identity matrix. So if we could find such a matrix, then solving this system of equations would just basically turn into a matrix multiplication, right? We could just take that matrix A inverse, multiply it times B using the kind of the formula we just saw, and we would get V equals A inverse B. Okay, so that's a nice idea. And then the kind of question is, you know, when can we find such an inverse matrix, and how do we find it? Well, if A is an n times m matrix, there will be a unique solution of this form whenever the columns of A comprise a basis for Rm. And that comes from kind of the fact that we were seeing earlier, which is that we need the columns of A to sort of span the whole space in order for there to be guaranteed that there is a linear combination. And we need them to be a basis. We need them to be linearly independent. Otherwise, there's sort of degeneracy here. So to find a unique solution, we need those columns to comprise a basis for Rm. And then the kind of geometric picture that we saw sort of guarantees to us that there'll be a unique solution here. But we'll look a little more at that in a minute. So this is just kind of a restatement of what I just said. It's a really important kind of fact to keep in mind. In practice, we can write down formulas for the inverse of A. They're very cumbersome, and they're not really even worth looking at here. In practice, we compute inverses and generally solve matrix equations using numerical algorithms. So maybe you've used these algorithms in R anytime you've solved for a matrix. And it's sort of a kind of thing best left to numerical algorithms. But it is worth thinking a lot about when we expect there to be an A inverse and sort of being able to work with the inverse of A symbolically. Okay, so one other way of looking at matrices is as representing linear transformations from one vector space to another. So what's a linear transformation? A linear transformation is a kind of operation that maps a vector space into a different vector space. It encompasses a lot of the kind of mappings that you might dream up, like rotating the vectors around the origin, scaling them, you know, that is like stretching them, reflecting them, and the composition of these operations. The sort of formal definition for some function to be a linear transformation is that whatever this function is, it has to distribute over sums. And when we multiply, when we take the function of some scalar times a vector, the scalar has to come out of the transformation. So all of these operations that I mentioned up here satisfy this property. It turns out that if A is an n by m matrix, then the sort of multiplication A times x actually describes a linear transformation from the space Rn to the space Rm. So any linear transformation can be expressed this way, and any matrix can be thought of as corresponding to a linear transformation. So here's just a little picture. If we take some vectors and we map them now to a new space by multiplying by A. So we take the vectors that I've shown here, we multiply them by this matrix I show above. We get some new vectors. So this 1, 1 vector here kind of becomes gets sort of rotated and stretched. Again, this like -1 gets rotated and stretched. So we can see there's this composition of these different operations. So I just draw 4 vectors. Of course, there are infinitely many vectors in this space, and they all get sort of rotated and stretched and scaled by this operation. So this gives us kind of another meaning for the matrix inverse. If we take one matrix times another, what we're doing is we're basically just applying sequentially 2 different linear transformations. So we're like first rotating and stretching one way, and then we're rotating and stretching some other way. And in particular, if we take multiply by the matrix inverse, that matrix inverse is a new transformation that undoes the old transformation. So if we take, we first took our original vectors, we multiplied them by A to get this kind of new, to be mapped into this new space. Now if we multiply by A inverse, we actually just map back to the original vectors. Okay, so here's the inverse matrix. So again, this is kind of 2 rounds of matrix multiplication that takes us from our original space to a new space and then sort of back to the old vectors we started with. A linear transformation has, so we start with some vector space, we apply a linear transformation, and we're going to generate some new vectors, right? The set of all possible vectors, all the vectors that we can generate by taking this linear transformation is called the range of the transformation. So in this kind of picture, we start in this Rn space and we're mapping to this Rm space. And there's going to be some subset of vectors, potentially the whole Rm, but maybe just a subset that our initial vector space maps into. And this is called the range of the transformation. And the dimension of this range, so this range may be, again, the full space Rm, or it may be a subspace. And its dimension is called the rank of the matrix A, or of the associated transformation. And equivalently, that's going to be the dimension of the span of the columns of A. So if we take a look at the columns of A, the number of linearly independent columns of A, essentially. A very closely related concept is that if we take the set of all vectors in our original space such that A times x is equal to 0, this is called the null space of A. So these are all the vectors that get mapped to 0, basically, by this linear transformation. And the dimension of this space, so now this is a space that lives in our domain in Rn, the dimension of this space is the nullity of A. And a very important result in linear algebra that unfortunately we don't have the time to really prove or to do justice to is that the rank of A plus the nullity of A is equal to M, to the dimension of the space that we're mapping to. And closely related to both of these concepts is a characterization of when it's possible to write down an inverse for a matrix A. So A is invertible, that is, it has an inverse, if and only if the linear transformation associated with it is 1-to-1. So if every vector in our kind of initial space has a unique vector in the range that it maps to. And basically, because of this rank plus nullity statement above, we can equivalently say that a matrix A is invertible if the rank of A is equal to M, or if the nullity of A is equal to 0. And one kind of immediate thing we should see here is that for any of this to really be possible, we need the N and M to be the same. So if we're mapping from a vector space of one size to a vector space of a different size, we're never going to have this 1-to-1 mapping. So what that kind of tells us is that only square matrices, only matrices that are n by n, are going to be invertible. Okay, so that's several kind of characterizations of when we expect there to be an inverse. And again, we're not really getting into the computation, but that's okay. But none of these are really sort of practical criteria that are easy to check, right? They're kind of nice ideas, but how do we actually sort of check if a matrix is invertible, if it's what its rank is or what its nullity is? Well, one way to do that is to use a kind of fundamental summary statistic for matrices called the determinant. The determinant of A is a kind of nice number that shows up everywhere. It kind of describes in a kind of hand-wavy way how volumes are scaled under the linear transformation associated with matrix A. But it has one really important property that relates to our question about inverting matrices. And so here I'll just show you a little example. So there's an analytical formula for the inverse of a 2x2 matrix that's actually not too bad to write down. I wouldn't recommend trying to write it down for any bigger matrices. But a 2x2 we can do, and it's just on the right here. And you'll see that in this formula, 1 over the determinant of A appears. Okay, so this number determinant of A that is basically a polynomial in the entries of A. In general, it's a kind of complicated polynomial. So again, I recommend, usually we just use sort of numerical algorithms to calculate this number. But in any case, it appears in these formulas. And so here, this might lead us to suspect that the inverse of A is not defined when the determinant of A is 0, right? Because then this becomes 1 over 0. And this is just kind of a hunch that we might develop, but it turns out to be a generally true fact. So a matrix A is invertible if and only if the determinant of A is not equal to 0. And again, there's a kind of nice formula for the determinant for 2x2, but quickly the formula becomes quite complicated as we go to higher dimensions. Okay, and so now that we kind of have the determinant in hand, we get to our final topic that we're going to have to treat a little quickly, my apologies, which is really one of the most important in linear algebra, which is the idea of eigenvalues and eigenvectors, so the eigenvalue problem. So the kind of question we're trying to answer in the eigenvalue problem is which non-zero vectors have their orientation unchanged under linear transformation. So I take some vectors on the right here, and I apply some linear transformation. They get mapped into new vectors. A few of them, very special ones, don't change their direction. They are only scaled, right? So this vector that was originally pointing up gets kind of rotated and stretched. But this vector that's following the 1, 1 line just got stretched and not rotated. And so the eigenvalue problem asks which are these kind of special vectors that just get stretched. And kind of more symbolically, we have this eigenvalue equation, which is A times x equals lambda x. And this lambda here is a scalar that we call an eigenvalue. And these x's are sort of unknown vectors. So we want to figure out what are solutions, what are x's and lambdas that make this equation be true, that make it true that the multiplication by A just returns us the original vector we had, possibly scaled, kind of stretched, but not rotated or reflected or anything like that. So these unknown vectors are called eigenvectors, and the scalar here, lambda, is called the eigenvalue. And okay, so we can try to solve this problem. And what we might kind of naively do is to say, okay, well, let's get all this stuff on one side of the equation. So we can take our AX, subtract lambda x. So we get this equation on the second line, AX minus lambda x equals 0. And then what we might do is we might say, okay, well, let's factor out the x, that vector x. And to do that, because we're doing matrix multiplication, and here we have to be a little bit careful. When we factor out the x from this scalar, we need this scalar like lambda to still kind of be compatible with addition with the matrix A. So we get lambda times the identity matrix, right? So this A minus lambda times the identity matrix times x. If we distribute this x, we get back the equation above. Okay, so now this is really a matrix equation, sort of like the ones we looked at before. So we have a matrix, A minus lambda identity, times a vector x equals 0, which is a vector of zeros here. So it's just some target vector, like we talked about before. But it's not quite as simple as before, because we noticed that 0, the vector x equals 0, is always kind of a trivial solution that solves this problem. Okay, but we're not interested in that trivial solution. We're interested in non-zero vectors. But if this matrix A minus lambda identity is full rank, then the discussion we just had tells us that 0, because 0 is a solution, it must be the only solution, right? Because the mapping would be 1-to-1. So that would imply that if 0 is a solution, it's the only one. And so what that tells us is if we want to find sort of non-trivial solution, non-zero x's, then we need this matrix A minus lambda identity to be singular, to be non-invertible, because we need the transformation now to be not 1-to-1. So that's actually kind of nice, because it tells us that what we need is the determinant of A minus lambda I to be equal to 0, right? That's the criterion we just mentioned for a matrix being non-invertible or singular. And this expression here, determinant of A minus lambda I equals 0, is called the characteristic equation for A. The left-hand side is a polynomial of degree n, which we call the characteristic polynomial. So again, this determinant here, there's a sort of formula for it, and it's going to be a big degree n polynomial in the entries of the matrix inside. But then now we can just sort of apply some results from algebra. So if we have a degree n polynomial, that equation is going to admit n solutions, n roots, if we count them with multiplicity. We count repeated roots potentially. So there are up to n distinct solutions, n distinct values of lambda, and each value of lambda comes with a kind of associated x, an associated eigenvector, and we call these together an eigenpair. But one important caveat is that we have to admit complex eigenvalues and eigenvectors potentially, right? So as soon as we start having an n degree polynomial, even if it's just a quadratic or something, it might have complex roots. And we have to allow that. Kind of geometrically, we can think about that as like, there's no guarantee that a linear transformation has real eigenvectors. And one example is, I mentioned that rotation is an example of a linear transformation. So rotation would be like, take a vector space, rotate every vector by 10 degrees. If we did that, it's fairly obvious that there is no, there's going to be no vector that's doesn't have its direction changed, right? So in that case, there will only be complex eigenvalues and eigenvectors. If our matrix A already is non-invertible, so matrix A on its own has a rank k less than n, then there are going to be 0 eigenvalues. So basically, there are going to be v's, choices of v, or eigenvectors, such that A times v equals 0. So basically, if we go back to our characteristic equation, we don't even need this lambda identity to make determinant equal to 0. So there are just choices of eigenvectors that already kind of satisfy that equation. So those are going to be eigenvectors with associated eigenvalues of 0, and the rank is going to be equal, the rank of the matrix will be equal to n minus the number of 0 eigenvalues. So this gets us to our final kind of big laundry list of statements here that is worth spending a little bit of time thinking about. But hopefully, at least very quickly, we've discussed the ways that all of these statements are equivalent, right? So A being invertible, the columns of A forming a basis for Rn, this system of linear equations having a unique solution for any B, the columns of A being linearly independent, the determinant of A being non-zero, the rank of A being n, the nullity of A being equal to 0, and A having no 0 eigenvalues. So I think we're just about out of time here.
Yes. So go ahead. Go ahead. We have 5 or 10 minutes more, if you need.
Okay. So one last is that that's kind of, so that's the eigenvalue problem in a nutshell. And I mentioned that the eigenvalue problem has potentially n distinct eigenvalue. I mean, n distinct solutions, basically, n distinct pairs of eigenvalues and eigenvectors that satisfy it. And so we can imagine collecting all of those eigenvectors as columns of a matrix Q, so shown down here, and all of their associated eigenvalues in a diagonal matrix lambda. So again, this diagonal matrix is just a matrix that has like AII or lambda 1, 1 equal to something, or something non-zero, lambda 2, 2 equal to something non-zero, and all the off-diagonal elements equal to 0. So we can form these two matrices, okay? And if we form these two matrices, we have now this kind of bigger matrix equation, A times Q equals Q times lambda, that unfortunately, I don't think we have time to really kind of walk through the multiplication of these things, but this is a way to sort of simultaneously write all of the solutions to the eigenvalue problem. So that formulation that we had before, AX equals lambda X, this is a way to sort of write all n solutions to that at once. And we can see that if this matrix Q is invertible, if it has an inverse, then we can multiply by that inverse to get down below A is equal to Q times this matrix big lambda times Q inverse. So again, this is only possible when Q is invertible, and that's only possible when, you know, one of those many characterizations holds true. So what it really means, or one thing it means, is that we must have n linearly independent eigenvectors. Okay. When that holds true, we can write A in this way. And what this tells us is that the matrix A is completely specified by its eigenvalues and eigenvectors, right? It can be written solely in terms of its eigenvalues and eigenvectors. So this question that we started with that looks sort of like kind of a funny question ends up being a complete characterization of a matrix. And so if we know all of the eigenvalues and eigenvectors, we know the matrix, we know everything about it. But the eigenvalues alone actually are often highly informative about a matrix. So the set of eigenvalues is called the spectrum of A. And in many cases, for example, in biology, in looking at different models, dynamical systems, the eigenvalues alone of A contain a lot of rich amount of information about A. So an important example that I'm sure you will see in these talks if you haven't seen before, and this is just to give you kind of a little hint of the value of thinking about these eigenvalues and eigenvectors, is that if we have a matrix difference equation like xt equals A times xt minus 1 plus b, so basically a system where at each new time we get the state of the system by multiplying the old state by a matrix. This kind of system converges to an equilibrium if and only if the maximum absolute value of the eigenvalues of the matrix, which is called the spectral radius, is less than 1. Very closely related to this, the matrix differential equation dx dt is equal to ax plus b, which is again a very kind of general, very sort of useful model, converges to a steady state if and only if all the eigenvalues of A are negative. So these are cases where just knowing these n numbers is kind of totally sufficient to tell us about the behavior of a system that really has n squared parameters that's governed by this whole matrix, but these eigenvalues are actually sort of incredibly rich source of information about it. All right, so I'll stop there. Apologies.
No.
Over by a few. I don't know if there's time for any questions.
Yes,
I
I think we have like 2-3 minutes for questions, and then we can take a short break before the next lecture. So please, if you have any question, you know how to ask it. Either post it on the chat or raise your hand. So there was a question a little bit back on the eigenvalue, asking if the scaling factor that it appeared in equation was the eigenvalue. Yeah, you can ask the question, Shamoli. Yes.
Hi, in one of your slide, you showed that, yeah, the direction remains same, but only the rotation of that vector changes. And that's for the eigenvalue, no? You showed that.
Yeah, so like in the slide that I have here, so these
so
vectors.
The eigenvalue lambda is the scaling factor here?
Yes.
The
yeah.
magnitude?
Exactly, yeah. So the lambda is for the eigenvalues, the lambda is the scaling factor.
Okay, thanks.
Yeah. Yep. Yeah, so just for example, like in this picture here, this vector like 1, 1, or this vector, sorry, starts as 2, 2, and it becomes 3, 3. So the one of the eigenvalues of this matrix is 3/2. It's scaled. These vectors become scaled by 3/2 when we multiply by a.
Yeah.
There is another question by Augusto saying, how do we determine the eigenvalue of a rectangular system if it is even doable?
That is an excellent question. So yeah, I actually kind of omitted that. So right, for this kind of interpretation that I gave, where this vector has its direction unchanged under multiplication by a, that really implies that that the matrix must be square, right? If this vector on the left has a different size than the vector on the right, then it doesn't even really make sense to talk about the orientation being unchanged. But that said, there is an analog to the idea of an eigenvalue for a rectangular matrix. And that is, if we take now the matrix A transpose A, so this matrix is, we can think of as kind of like a covariance matrix of A, but it's a matrix related to A that now will be square. And so being square, it will have eigenvalues. And so we can look at the eigenvalues of this matrix, which is related to A. And these are called the singular values of A. And they, the theory of the singular values of A is a little bit more complex, so we don't really have time to get into it, but they kind of tell us much of the same information as the eigenvalues would. So yeah, if you're interested in learning more about that problem, the thing to look into is the singular values of A, or the singular value decomposition, which in many ways is sort of analogous to the eigenvalue problem.
Thank you.
Okay, so is there, well, I think, well, let's answer the last question by Dabasmita, and then I think we can take a short break, stretch legs, get a cup of coffee, and before the next lecture. So Dabasmita asked, what happens if we get an eigenvalue equal to 0? What will be its geometry representation?
What will be its what, sorry?
It's geometry, I guess it's geometrical representation.
I see. Yeah, so an eigenvalue equal to 0 is basically a direction. So this matrix A is a direction where the multiplication by A just maps us to 0. So we can kind of think in this picture that if this eigenvalue for, say this direction here was 0, when we multiply by A, the matrix would just become I mean, the vector here would just become 0. So we would kind of just map to the origin. So these are directions where multiplication by A just kind of kills the vector that's there. And what this tells us is that X is in the null space of A. So yeah, I'm not sure if that's, hopefully that gives some sense of the geometry.
Okay, great. So I think is a good time to stop. Thank a lot, Zach, very much for the very nice tutorial, which again it will be available on YouTube for the next generation to come. So thanks again also for doing that very early in the morning. And of course, what we're going to do now is to take a 4 minutes break. We're going to be again randomly assigned to breakout rooms. So feel free to chat with whoever you are assigned to, or to take a break, stretch your legs, and we'll be back in 4 minutes. Thank you very much.
Thank you.
Hey, Zach. Good morning.
Hi, Stefano.
Hey, Stefano.
Good job. So I caught only the last few bits, but thank you for doing
your favorite
that.
part.
Yeah, my favorite part. That's great.
Just to mention that we are live stream on YouTube, so whatever. I mean,
hello, world.
Yes. So I think we should be divided in breakout rooms. This hasn't happened yet, but well.
I open the breakout rooms.
Yes, please.
Okay.
Yes.
Hello.
Okay, so I think we are gonna be back in minutes or so. So then takes a minute for people to leave the breakout rooms. So in the meanwhile, I can remind to the people that are watching on YouTube that they can post their question in the chat, and I'll read it on your behalf. And also I'll pass the link to the lecture notes of the next lecture by Stefano Lesina in the YouTube chat. So you can also get the material there. And let's wait for the people on Zoom to join back, and then we can start. Okay, so I think people are back. Great. So before I introduce the next speaker, just the usual info about Netiquette. So if you want to ask a question, please either post it in the Zoom chat or use the raise hand tool on Zoom that you can find under participants. There are 3 dots and you can raise hand. And when I think Stefano will stop every now and then to leave time for questions, then I'll sort of give you the possibility to talk, or I'll ask the question on your behalf. And another point, I saw in the breakout rooms that there are many people that are alone in a room waiting for others to join. If you have the version Zoom 5 installed, which you can install for free, you have the possibility to change rooms. So if you are alone and there is no one to chat with you, you can also change room and find someone else to chat with. So great. So after this, it's my great pleasure to introduce the next lecturer, Stefano Lesina. Stefano got his PhD from the University of Parma, and after a postdoc at the University of Michigan and at Nancy's, he moved to Chicago, where he's currently a professor in the Department of Ecology and Evolution. His most recent research has been focused on the theoretical understanding of large ecological communities, and he will give 3 lectures on the theory of ecological assembly. So thank you very much, Stefano, for being with us. And yes.
Thank you, Jacopo. Good morning, good afternoon, good evening, everybody. So my name is Stefano. I'm broadcasting from the beautiful campus at the University of Chicago, where the weather is nice but a bit cold. And yes, I have 3 lectures on some sort of like theory of assembly of ecological communities. These 3 lectures, unfortunately, are not exactly the same length. So don't worry if we cannot go through the whole first lecture. The other ones are a little shorter. So we'll see, we'll take it as it comes. So I have very extensive lecture notes that I'm posting on GitHub. I actually put the link to the lecture notes and the GitHub repository in the chat. And the idea is basically that you can build all these lectures on your own computer. And in fact, you can play with all the code that is provided. To do that, you need to install R, and then you need like these packages, right, that will be needed for the calculations. In terms of questions, like that Jacopo was discussing before, I would like maybe divide them in 2 categories. The first category is questions that are really like needed for understanding what's going on. So if Jacopo, that is manning the chat, sees anything that means like people are not following, then just interrupt me. And in fact, like somebody already saying, I cannot download the lecture notes. So like if you click on this link, right, that it's provided, and then you go here in code, and then you say download zip, you can download the zip file with all the lecture notes. And to see the lecture notes, you can just put this address that I put in the chat in your browser, and you should be able to follow the lectures. I follow these lectures religiously because I wrote them especially for these series of classes. And so you should be able to follow precisely what I'm doing. Then there's other types of questions which are like curiosities or like extensions or things like that. Those I will try to keep for maybe the last 5 minutes or so. All right, that said, we can get started. And I just give a very brief, very partial overview of the history of ecological assembly. What is ecological assembly? It's simply like the process by which ecological communities are built. So you can imagine that there's a process by which species enter in a certain system, right? Increasing the richness, like the number of species in the system. And then there's the opposite process, which is like extinctions, by which some species disappear from the system, right? So the interplay between this kind of colonization, invasion, or like immigration and extinction create like some sort of balance by which we build these ecological communities. The typical setting actually is something like this, right? That we have some sort of mainland or like meta community. Imagine like a bunch of species, and here each species is a different like symbol. And then every so often we have this immigration event, right? Like this idea for which like a certain species, say these diamond species, enter the system here in this island or local habitat or however you want to call it. And now these two species, for example, can start interacting. And what is the outcome of this interaction? Maybe these two species will coexist in the local habitat / island, or maybe one of the two will go extinct, or maybe both of them will go extinct, right? So we have different outcomes. And then after a while, maybe this other species like triangle comes back into the system, and then again, we restart the dynamics. So this is basically the idea of this ecological assembly. Historically, this type of island, mainland type of model has been contrasted with other models that instead are based on species traits. So now we're thinking there is a certain environment, this environment, a certain condition, you can imagine like temperature, right? And so maybe some species will thrive at this temperature because of their traits, and some other will not be able to grow. And as such, what the environment does is impose a sort of selection on the traits of these species. So typically these models are more focused on traits of the species rather than their identity. And this process by which the environment selects for certain species and not others is called environmental filtering, right? And so you can read a lot about environmental filtering, and this typically leads to what? To the fact that we're selecting for certain traits, right? So the traits will cluster together, something that we call trait under dispersion. Now, of course, species can interact with each other, right? And imagine that we have a community of competitors. Then these competitors are competing for the shared resources, and as such, they cannot really coexist if they're too similar in their requirement of their resources. And this would lead to what? To a separation of the traits of the species. So the opposite of like this convergence that we were seeing before, and this is called over dispersion. And again, this is like a view of this assembly based on traits rather than on species identity. These themes went on for basically forever, like as long as the discipline of ecology. And in fact, like I put here like a book that is like 25 years of discussions on assembly. And reading this book, I was really like taken by the introduction, because the introduction, I suggest reading it, like maybe without too many prejudice. But it is a very forceful introduction and somewhat bizarre. And in fact, that immediately after I found this review by Nick Gotelli in 1999, that again picks up on this introduction, saying that the language of the introduction is an embarrassment to the discipline, which also tells you that not only this is a very old problem, right, that of the ecological assembly, but it's in fact one of the most debated, heatedly debated problems in ecology. If we go back in history, as I was saying, this is very old history, we can find examples in 1899 when Henry Coles, actually he was at the University of Chicago, and he developed this theory that we call the theory of succession, by looking at the Indiana Dunes, which like are basically half an hour south of my office on the shore of Lake Michigan. And so you have these sand dunes that you can imagine like start building up. And what happens is that some species land on these like sandy dunes and are able to colonize these sandy dunes. We call these the pioneer species, right? And by doing this, they stabilize these dunes somewhat, and they allow for other species to come in, right? And so we have this kind of sequence of species coming in and replacing, in fact, each other to some extent. And what is very interesting is that because there's so much like wind in Lake Michigan, every so often these dunes are blown out, and so the process restarts. And you can basically date the dunes. How long is this dune been developing for? By looking at the vegetation. So what you can really do is some sort of like substitution of space for time, right? Like that by looking at different places, I can see dunes of different ages. And as such, I can basically reconstruct this succession of vegetation along these dunes. And Coles, and in fact, like even other people like Clements, held this very strong view that this was somewhat of a regular, ordered, deterministic process, right? Like that there is like this sequence that each dune follows pretty much with some fidelity, like the same sequence of vegetation. This is in very much of a contrast with, like, for example, the view of Gleason that in 1920s started advocating for a much greater role of chance, right? So a lot of the debates we will see, like Democritus, like the Greek philosopher, would be pleased that a lot of these discussions are chance versus necessity, right? Like that a lot of these as this very basic philosophical point at the back. Another case like of something that created a huge debate in the literature is the work of Jared Diamond, who was studying avian, like bird assemblages in island off the coast of New Guinea. And what he noticed is that certain combination of species were never observed. He called these forbidden combinations. And the idea was that these were prevented from happening by competition, for example. And the idea there is like, now if I look at all the islands, right, and I look at all the possible patterns, and I see which one are forbidden, maybe I can learn the rules of the game of assembly by reconstructing it like in this inverse way, right, of looking at all these combinations and then finding what's going on in the background. This work, needless to say, caused an intensive debate, like what is called like the null model wars that occupied ecologists for a lot of like the 1980s and 1990s. And again, are these patterns that we are observing the outcome of some deterministic necessary process, or rather they arise by chance? And this actually led to a fantastic like development of null models of like, what should we expect when we have a certain number of species interacting? With which probability are we going to observe these particular like sequence of presences and absences? And this work was spearheaded by Dan Simberloff, Connor, Gotelli. There are very, very good reviews. I'm pointing here to a book on null models in ecology. Again, like chance versus necessity, if we look at the early 2000s, like the work of Steve Hubble on neutral theory, right? What should we expect if species were simply not to interact or were somewhat equivalent? In that case, like what we observe in terms of pattern, for example, species abundant distribution, would be basically driven by stochastic fluctuations, right? Species would take a random walk in this space, and then we would end up with some sort of like statistics. And sure enough, like the statistics that we can observe and measure in nature are somewhat compatible with this assumption of neutrality. And again, this sparked an immense debate facing like neutrality versus, again, like necessity, represented here by niche dynamics, meaning like these are driven by species interactions, like competition, like trade, like avoidance, in fact, of competition to some extent. Finally, I'm just gonna, as you can see, like here you have like readings for several years of studies. Another idea that kind of came out of this assembly is the idea of community phylogenetics, right? We know that we can reconstruct to some extent like the evolutionary history of species, and that this evolutionary history gives us a lot of information on what happens in terms of traits and resource utilization and whatnot. And such, like what you would think is that you can relate phylogenetic data, for example, phylogenetic trees, with a community ecology, right? And so this idea of community phylogenetics is exactly centered on this. The history of community ecology from like late in the 19th century up to today. What I'm going to do today is actually take like some sort of like an older view. This is like models that were developed when I was, say, in high school, you know, like or early in my college years, and so we will examine some sort of a basic model of ecological assembly, and we will try to ask some sort of intelligent questions, and for which we can get an answer when we make a certain number of assumptions. For our exploration, just to keep things simple, what I would like to use is like what is arguably like the simplest model for population dynamics, which is like the generalized Lotka-Volterra model. Maybe you've seen it in a different form. Let me just write it in component form first. So this it's one of like the 6 equations that we teach all the ecologists in the world, right? So we're following like the density of population, say I at time t, and we're following this population in time. So we write a differential equation. And typically what we write is like xi, so the population density itself, times ri. Ri is what? Like it's the intrinsic growth rate. You can think of this growth rate as like the growth rate that this population would have when grown alone at very, very low density. This, in fact, can serve as 2 purposes, like a growth rate if this is positive, or a death rate if this is negative, right? If I put lions, you know, like in a nice field with no animals to eat, they will die. And then we have the interaction part, like these species interact with all the other species to some extent in the community. So we take like the sum over j of aij, and then the density of species j at time t. Right, so this is like in component form. I rather prefer writing this in matrix form, which basically say this is a vector now of growth rate, dx dt, and d of x here with big D means like a diagonal matrix with x on the diagonal. And how come that I have all these things written here? And then R now will be what? Like a vector of growth rates, of intrinsic growth rates, and A is now a matrix of interactions. Okay? And I assume there are n species, and like I just labeled the species from 1 to n in whatever order you prefer. All right. So for a single species, and maybe you've seen this when you've done the tutorial on nonlinear dynamics, this model can only have very, very few outcomes. They're not especially interesting. So a species by itself can either grow exponentially, it can decay exponentially and then go extinct, or it can reach some sort of an equilibrium, like some level at which it stops growing or shrinking. When we include 2 or more species, we can have like cycles, neutral cycles, or even like limit cycles that could even be stable, like meaning attracting different trajectories to the same limit cycle. And with 3 or more species, we can even find chaos, like chaotic dynamics. So I have code in the repository that you can download to integrate like the dynamics of this model. And here I'm just loading a particular example that I found just like by searching, in which we have a certain matrix of interaction A and a certain growth rate R, such that when we integrate the dynamics, what you see here is that this species keeps cycling for forever. Like this is a good example of a limit cycle, right? So the species will not stop the dynamics ever. They will oscillate up and down in this fashion for forever. Okay? So this is one of the cases of limit cycle. You can find similar cases with like chaotic dynamics, which you can think of as like cycles that, however, never close on themselves, right? They're non-periodic cycles. All right. One thing that we can do in this model, which is in fact the simplest thing that we can do in this model, is to look for fixed points, right? So are there particular densities of the species? Imagine like a vector of density such that the dynamics at that point are fixed, right? They stop like moving. And because of the form of the equations, right? Like what do we have? Let me maybe put an annotation here, right? So our equation is like d of x times r plus ax. And this has to be 0 for the dynamics to have stopped. And so you can see that there's basically two cases. Either this part is 0, right? Like the part we multiply something by 0 and then it's 0. Or the part within the parentheses is 0, which is more interesting, right? Because in this case, the species might be present at a positive density. So then let's try to find the solution. The solution exists when this matrix A is not singular, and I've seen that Zach just taught you like a bit of linear algebra, so now you know what I'm talking about. And so basically we want to solve A of x plus r is equal to 0, which we can write as A of x is equal to minus r. And so like what we would like to do is to somewhat divide by this matrix. Of course, you cannot divide by a matrix, but what you can do is to multiply by the inverse of this matrix both sides, and then you find the solution, right? You find the solution as long as this matrix is not singular, meaning there's no 0 eigenvalue. Now we get a solution. It could be a solution that contains some negative numbers, and even for a theoretician, I've never seen -3 turtles or like -7 elephants, so these would not really be a feasible solution to our system, because like species have to have positive or at least non-negative density. But if such a point exists, right, so if we have a solution for the system that is all positive components, we call this a feasible equilibrium for the system, and it is unique, right, because we're solving a system of linear equation that has a single solution as long as A is not a singular itself. In R, right, you have code in R to do what? To solve like the system, you know, if I want to solve AX is equal to B, I can call solve of A comma B, right? And so we just do that with A, and RB is going to be minus R, right? And so if we do this for the system above, like the one with the limit cycle that we had above, what we find is that there is a positive feasible equilibrium, right? And so these are like the numbers here. And in fact, if you go in the plot again, these horizontal lines that are dashed here, this is exactly the solution of this thing. And you can see like that, for example, this purple species oscillates up and down, and the equilibrium is contained in the range of this oscillation. And the same is true for green, the same is true for red, the same is true for blue. Okay, that kind of gives us some idea of what's going on. In fact, you can even do a little more. I didn't include like the theorem or the proof here, but you can see Hofbauer and Sigmund, the book that is referenced here. You can show that to have coexistence of a certain number of species in generalized Lotka-Volterra, you have to have a feasible equilibrium in the interior, right? So you have to have a point where all the densities are positive. That is an equilibrium for the system. Now, this equilibrium might be stable or unstable. And of course, like to have, for example, limit cycles or to have chaos, you need like an unstable equilibrium. While if you want to have all the dynamics to all the trajectories to converge to this point has to be stable. So next, what should we do? We should think about stability. So have you covered like local stability analysis? It's my question for Jacopo or for whoever can answer in the notes, or should I go over it like?
We have, I mean, it was discussed in one of the tutorials, but I think it's always good to, I mean, very quickly remind the audience.
Right. So just like as a reminder, because you already should know about this, but maybe you forgot. So we have a fixed point, right? So we have some point at which like dynamics are stopping. And what we want to do is to say, okay, but are trajectories that start very, very close to this point gonna converge to this point, or rather they're gonna spiral away and some species will go extinct, right? So if we want to have like coexistence at an equilibrium point, it better be attractive, right? Like you should have like that if you perturb the densities of the species a little bit, nothing much is gonna happen. And the way you do this type of analysis, in fact, is to take like the system, put it at equilibrium, and then tailor expand around it, right? Like, and if you tailor expand like the dynamics, so imagine that I'm saying just like something like I want to track in time. let me just put an annotation. I want to track in time what? The perturbation, say dx, d of delta x in time, right? So imagine this delta x is like my equilibrium plus minus some very small quantity. In fact, infinitesimally small quantity. And then if I Taylor expand this, what do I get? Like I should first put like my equations, right? This would be the generalized Lotka-Volterra equations evaluated at the equilibrium, but this is 0. And then we would get what? Some sort of Jacobian matrix evaluated at the equilibrium point times my perturbation, and then plus some higher order terms, right? And let's say that we don't care about the higher order terms because around like an equilibrium, if the perturbations are small, everything looks like a linear system. And so then you can see that we have like, this is 0, these we removed. So we end up with just like this Jacobian matrix. And this is a linear system of differential equation, which we can solve. And what you can show is that this Jacobian matrix at equilibrium has to have all the eigenvalues with negative real part for this equilibrium to be attractive, right? So that's the idea of local asymptotic stability. If that's the case, provided that we start arbitrarily close to the equilibrium, eventually like these trajectories will either converge to equilibrium or at least not move away from the equilibrium. So we're left with the way of writing like this Jacobian matrix. And so call f of I, you know, just like the Lotka-Volterra for species I. What we need to do is to just take like the partial derivative with respect to every other species. That's the definition of a Jacobian. And if you do that, you find like that we have for the term ij in the Jacobian, we will just find aij times xi. And then we have a slightly different formulation for the diagonal elements of this Jacobian. Right now we're deriving with respect to xi. And so we find like the growth rate for species I, the interactions with all the other species j, plus another term that comes from the fact that this is really a quadratic equation in I, right? Like because we have something on the diagonal multiplied by xi, and we have xi outside like the equations. And as such, we get this quadratic term, and this would lead to this extra term AII-XI. However, at equilibrium, what do we have? That this is, in fact, what's inside the parentheses, right, when we write our system like that. And we're saying this is 0, but this is exactly the same term. So this whole thing is 0. And therefore, we end up with something very simple. You see, like the element ij is aij xi or aii xi, which then means what? That we just have like the matrix of interaction A, and then we multiply each row of this matrix by the corresponding equilibrium when we evaluate these Jacobian at equilibrium, which means simply like that we substitute to every xj and xi their equilibrium value. So then this Jacobian is especially simple for the Lotka-Volterra model. And we know that this Jacobian evaluated at equilibrium, which is called in ecology the community matrix M, has to have eigenvalues with negative real part. So now I have a question for you, which is, what do you think will happen? What would you think will happen to the Jacobian in the case of the limit cycle we've seen before? Right? We said like this, there has to be an equilibrium point. We actually found that there is a feasible equilibrium point. It was sort of in the middle of all these oscillations. But if it were really like stable, as long as we get like through this cycle close enough to this equilibrium, it will converge, right? And then we would have just like fixed densities from then on, right? Which means what? That this equilibrium should be unstable. All right? And in fact, like we can do the same that we're doing here mathematically. We take just like x star, like my equilibrium to be the solution of the system with a and minus r. Then we create this matrix M by multiplying a diagonal matrix of x stars times, this is like the way R does like matrix multiplication A. And then we can look at all the eigenvalues of this matrix M and see whether all of them have negative real parts. Now, in ecology, we mostly are concerned with what? With matrices that contain real numbers, right? Where all the coefficients are real numbers. A matrix with real numbers has only basically two types of eigenvalues. These eigenvalues can either be real numbers themselves, right? So imagine like numbers on the typical number line that we think about, or they could be complex numbers. But when they are complex numbers, they have to be paired, right? What I mean is that you can just like draw these eigenvalues in the complex plane. So imagine that this is like my real part of the eigenvalues. This is my imaginary part of the eigenvalues. And so every complex number is mapped into this plane. And so my eigenvalues could be either be real numbers, right, which would appear here on this line, or if they're complex number and I have a number here, I have also to have another here, right? So like they have the same real part and imaginary part with opposite signs. And so let's look at these. We have only 4 eigenvalues here, right? And so these one, for example, you can see that there's no imaginary part. The imaginary part is 0. So this would be a negative eigenvalue that would be somewhat here, let's say. And then we have 2 paired complex eigenvalues, right, that have positive real part here, 0.37. And then they have like imaginary part that are coupled, 2.06 and minus 2.06. And finally, we have another real eigenvalue here, minus 0.61. Are all the real parts of these eigenvalues negative? No. Therefore, this equilibrium that we had for the limit cycle is locally unstable, right? Like if I start even close enough to this trajectory, it will not go back. In fact, what will happen is that it will move away from the equilibrium, at least initially, with a speed that depends on these eigenvalues, right? The smaller, the slowest, in the direction that will be the one given by the eigenvector corresponding to this eigenvalue, or in case of like complex numbers, like there would be 2 eigenvectors that determine these oscillations away from the equilibrium. All right. So just to say, this is how we would go about doing local stability analysis, and we will see in a second a way to do even stronger stability analysis. But before we go there, I just wanted to show that this equilibrium is in fact very important in Lotka-Volterra, much more so than in other models, because when we have dynamics that are not like fixed point dynamics, right? So imagine that instead of like converging all these trajectories of the densities of the species in time to a point, they say oscillate or they have some chaotic dynamics. The equilibrium, even though it has to be unstable, and we just saw an example of that, it still contains a lot of information on the system. And in fact, it provides us with like the average density of the species in time, right? And to do this, what you can do is like just to say, let's take the average in time of the density of each species, right? And we can just write this as this integral. And to make things much simpler, what we're going to assume is that we're in some sort of cycle, right? And that we choose like time 0 to be when we start like this cycle, and time t, when do we end this cycle, such that, you know, after a certain time, big T, we're exactly in the same place where we started, right? This will make things a lot easier. All right. And of course, we're interested in what? In cases in which like this x of t is always positive, right? Species don't go extinct in this cycle because otherwise they would not be part of the cycle. And as such, we can assume that all these numbers are positive. And if all these numbers are positive, we can take the log of these numbers, right? So we can take the logarithm. And in fact, we can write an equation for the logarithm of xi of t in time, right? And the way you would do this, like, is what? D of log x dt is simply like dx dt divided by x. So it's very easy. So we can divide each equation by xi of t. And so what you can see is that this just like gets rid of the part that we had in front of our equation, right? So if I write, let's another way to write this type of equation that is a little more compact is to say x dot is dx dt is d of x times r plus ax, right? And so now we want to take the log of x in time, right? Like this is going to be x dot divided by x, and as such we get rid of this x, right? So we get r plus ax. Okay, so that's like very convenient. We will use this trick again later. All right, so that's like our equation in vector form. Now what we can do is to integrate both sides and basically take the averaging time of both sides. And so we just formally write this thing. You can see that here we have dx dt, and then we multiply by dt. And so here, like, the equation becomes very simple, because then we're just going to have like the logarithm of the species at time big T minus the logarithm of the species at time 0. But because we did this assumption that we start and end at the same point, these two numbers are the same, right? So the left-hand side of this equation is 0. And that's why this trick was useful. And now we have to integrate the right-hand side. And you can see that we're integrating R, which is like a vector of constants, so we can take that out. We can take out also the matrix A, because also that does not change in time. And so we end up with this right-hand side, like R plus A times, and now wherever we had a species, now we have the integral, or like the average of the species in time. And the way to solve this problem is to do what? Is to multiply both sides by the inverse of A, right? In fact, minus the inverse of A. And so we have that this minus A inverse R is what? It's the equilibrium, X star, right? And therefore, like, the right-hand side, which like becomes the X star here, like here in the first place, like where we have R, we have a minus X star. We bring it on the left side, and now this matrix A will be canceled by the inverse of the matrix, and so you recover exactly what you expect. Like, the equilibrium is what? It's the time average of the species in time. So that's why this equilibrium is so important for Lotka-Volterra. Not all models will give you like this beautiful result. In Lotka-Volterra, you can show that this holds also for chaotic dynamics. Of course, taking like the average of something that is non-periodic is a little more difficult, but you can think of some sort of long-term average, or like the average will converge to this number. And now let's take the dynamics of the limit cycle that we had before, and then we can discard the first part of the dynamics. Let me just show you like the figure again, so that you can see why are we doing that. So you can see that we have some sort of initial dynamics that are a little different from the rest. And then it settles in something that looks a little more regular, right? That the cycle repeats over and over. So this first part we call the transient dynamics, right? So it's like the way they approach some sort of attractor that could be a point, in which case we would have an equilibrium. It could be a limit cycle, in which case we have something like what's on the board, or some chaotic attractor, but we always have this initial dynamics. So let's discard those and then take the average of each species in time for the remaining part of the time series. And if you do that, even though like we only run this model for a certain amount of time, you can see that when we take the dynamics, remove the initial transient dynamics, group by species, compute the mean density, and then print it, what we get is this set of numbers, which you can see here. It's very, very, very close to the equilibrium that we had computed, right? So if we were to do this for enough time, right, for a longer time, then you would have exactly convergence to these numbers. All right, maybe this is a good time to ask Jacopo if there are any questions on this first basic mathematics of Lotka-Volterra.
Yes, so there is a question actually about the stability criterion, which is asking whether there are stability criteria for community matrices like the one you presented. So I guess where you have the matrix multiplied by the density.
Right. Yes, there are things that you can say. Actually, this is a good segue for the next thing. For example, so imagine that we have some sort of matrix A, right? And what we can ask is whether this matrix A has only eigenvalues that have a negative real part. And let's say, for example, yes, they have, right? Which means what? That if I were to choose certain densities, imagine that I choose like my D of X star, right, to be the identity matrix. Imagine that my equilibrium is all the species are 1, right? Then if I multiply the identity matrix here by any matrix, I obtain the same matrix, and therefore this equilibrium would be stable for this choice, right? If I could choose, like, for example, growth rates such that all the species at equilibrium 1. Of course, what happens is that depending on this axis, I might or might not have stability, right? So the stability does not only depend on the matrix of interaction, it also depends on the equilibrium, and therefore implicitly it depends on what? The growth rates, right, of the system. Is this always the case? Not quite, right? Like, for example, if I can take a matrix, if my matrix A has this property that A plus the transpose of A, right? So imagine that now we're taking a matrix, summing its transpose. What we're going to obtain is some sort of symmetric matrix. A symmetric matrix will only have a real eigenvalues, right? Because we will not have complex numbers anymore. Now, if this matrix, right, which is like basically the symmetric part of A, has only negative eigenvalues, what you can prove is that for any choice of X star that is positive, which is only the choice we're interested in, these will be stable. Okay? So in those cases, even though we can choose the R's however we want, and as long as these R's yield a positive equilibrium, then the equilibrium is going to be stable. So this is a much stronger form of stability. And in fact, this is exactly the condition for like having only a equilibrium dynamics. And in fact, like that's a way we are going to use right now to prove global stability. Any other question?
There was a question on actually on the introductory part.
Yes.
And you mentioned the environmental filtering and trait under dispersion. Mm-hmm. And the question is whether these terms are related to natural selection.
That's a very good a very good question. To some extent, yes, right? Like what you have in evolving population is that they try to adapt like to local conditions, right? Like by selecting upon like the variance that is in the population. Maybe there are some individuals that have a certain genotype or phenotype or something such that they're more likely to grow in a given environment. So that's basically the same mechanism, right, that would lead to that. Of course, like the time scale would be quite different, right? If I put a lion here, like on campus, like unless they eat like the students, they will not have time to really evolve, you know, a new diet based on something that is here, I don't know, squirrels, right? They just would go extinct. But it's exactly the same principle, at least. And then I see a question that says whether there is a way to determine whether there is a limit cycle based on eigenvalues, and Simon Levine correctly says no. Unfortunately, I would add no, right? It would be, my life would be much easier if that were the case. So to prove a limit cycle, what you need to do is something a little more complicated, which is to basically draw some sort of like a box, right, around like these points, and then prove like that the trajectories cannot cross this box, and in fact they're reflected back. Like that is like the way to show like that these dynamics will be contained in a certain space. And then if you can draw another little box now around the equilibrium and show that dynamics will always go out of this box. Now the dynamics are squeezed between two boxes, right? Like, so that's the basic idea of how would you go about showing like different type of dynamics. All right, now let's concentrate for a moment on the simplest type of dynamics, which are like equilibrium points, right? Like that we have trajectories and they do whatever they have to do. They oscillate up and down and whatnot, and eventually converge to some sort of an equilibrium. And in fact, this is connected with the question that we had before. So what we're gonna assume is that we can find a certain set of numbers, like imagine positive numbers that we put on a matrix on the diagonal. We call this diagonal C, such that C times A plus A transpose times C has only negative eigenvalues, right? So this is again a positive, a matrix that is symmetric and as such has only real eigenvalues. Imagine that all of these eigenvalues are negative, right? Then our equilibrium point, if it exists and it's feasible, it's automatically stable. And in fact, it's globally stable, meaning we can start the dynamics from any positive densities for all the species, and the dynamics eventually will reach this point. right? And as I was saying, like this is a very, very strong condition for stability, because it says if A is stable and this property holds, then any multiplication on the left by a diagonal matrix with positive numbers, meaning like the equilibrium, will not change the stability, right? This is called destability in the literature, right? So how do we do this thing of showing that all the trajectories go to a point? That is an interesting and difficult question. And in fact, there aren't very many methods, to tell you the truth, because the problem is what? We cannot really integrate these dynamics analytically. We cannot write the solution for this system of very many equations, like that are nonlinear. So it's not that I can just say, well, let's write the solution of these equations, x of t for any t, and then I just take t very large and show that it converges to the equilibrium, because I cannot write the solution. So what we can do is to use what is called the Lyapunov function. And the idea of a Lyapunov function is fairly simple, right? We have a system that we cannot write the solution for. What we're going to do is to write some sort of like summary statistics of all the species. For example, imagine I take like the sum of all the species or the variance of the species densities, right? And if I can write a function such that, let me maybe write here for myself. Right? So if I can write a function v of the dynamics, right, of x of t, right? This is my summary statistic. And if I have this property that this v is always greater or equal than 0, right? And then v of x star of the equilibrium is exactly 0. And then the derivative with respect to time of x of t is lower or equal than 0, let's say lower than 0, then what happens? We have some positive function, right? Like this number is always positive when we're not at equilibrium. It always decreases in time. It is 0 at equilibrium, which means what? That if we wait for long enough, these dynamics will reach the equilibrium point. So this is the basic idea behind a Lyapunov function. Now, how do we write a Lyapunov function for the generalized Lotka-Volterra model? One way to do it is, like, let's write it in component form. Like we're saying v is what? Is the sum over all the species I of C of I, which is like a constant that we want to determine, of the density of species I minus the density of species I at equilibrium, minus the density of species I at equilibrium times the logarithm of xi divided by xi star, right? So this part of the equation, you can see it's always positive, and it's only 0 at equilibrium, right? That's good. That's nice. And therefore, if we choose positive numbers here, it means that the whole function will be positive, right? Because we're multiplying by a positive constant, positive numbers, and we're summing them. So we're guaranteed to have this to be a positive function. How do you come up with this equation? That's an interesting question. Like, I like this book by Steve Strogatz. It has this quote that says that divine inspiration is usually required to be able to write this type of equations. This is actually goes back to the work of Volterra, and in fact, like Go has a wonderful paper on this in 1977. I can put maybe in the chat or add it to the next lecture for you, right? So now what we're left with is to determine whether this derivative with respect to time of v is in fact a negative, right? And for doing this, I think it's convenient just to do this in matrix form. Right, so we can write this in matrix form by saying there's like a sum. We can put 1 transpose for that of a diagonal matrix C, and then we have like what? Here we add x, so we get like x dot, right? This would be the derivative.
That's what?
Right, of this. And then this part is a constant, so it goes to 0. And then this part here, we would get just like minus a diagonal of x star, and then x dot divided by a diagonal of x. Let's write log of x dot. Okay. So now we need to do a little trick, which is to say, well, I want to get rid of the parameter r, right? So when I write my equation and I say x dot is equal to d of x r plus ax, right? But at equilibrium, I have that ax is equal to r, right? Ax star is equal to r, so to minus r. So what I can say right now is that then what? That this equation I can write also as d of x a, right? Now imagine that I'm just writing r like this way, right? So then I would get a of x minus a of x star, right? Which I get from here, because if I change the sign here, I get a minus x star. And so even more compactly, I can say d of x a times delta x, right? The deviation from the equilibrium. Okay, so with this at hand, what we can do is to go on with our derivation. And I think that then I'm going to stop for the day and just take questions.
Great.
Let me just finish this, Jacob, 1 second. So we have this. Then we can say 1 transpose like C. And then here we just have like what? A times delta x times d of x. And then here we have minus d of x star a of delta x. So you can see now we have like this matrix that is x, this matrix that is minus x. So we can write this as diagonal of delta x. 1 transposed C. And then we have diagonal matrix of delta x and then A delta x. And then diagonal matrices commute, so we can swap these two. And then we can multiply 1 transposed by delta x. So we get delta x transposed C A delta x. And so now, if this matrix C A delta x were to be negative definite, you know that for any negative definite matrix M, let's call it, right? Then we have that this is always lower and equal than 0, lower or equal than 0, and in fact is 0 only if delta x is equal to 0, which is our equilibrium condition. And then when we're doing this thing, we're basically summing like this term, right? C A component like ij times delta xi delta xj. And you can see that therefore, like we're always gonna sum this delta xi delta xj one time when we're doing the ij component, one time when we're doing the ji component. And as such, only the symmetric part of this matrix will matter, right? We can write exactly the same equation by saying delta x transpose, and then here we put Ca plus the transpose of Ca, which will be A transpose C divided by 2 delta x. And as such, if we can find constants such that this matrix, this whole matrix, let's call it M, is negative definite, then the equilibrium is stable, right? So that's how you prove a global stability in this case. And that's the derivation that you find here. All right, I think we should like wrap up here. And then next lecture, we will start thinking really about assembly and what makes ecological assembly difficult or easy to do. So let's take some questions.
Great, thanks a lot, Stefano. Sorry for interrupting you too early. So yes, so we have time for questions. So please, if you have them, just ask them. I think Simon, if you want to.
Yes, thank you, Stefano. That was a terrific lecture. I just wanted to go back as a philosophical question to something you said at the beginning about the neutral theory. And I don't disagree, but there's two sort of interpretations. One, in using the neutral theory, you're actually assuming that's the nature of the interactions, that they're stochastic. And the other is you're saying we know that they're details, but they don't matter at the higher level. The same justification, for example, for using a diffusion model for dealing with how animals disperse. And it doesn't make much difference for what you were talking about, but I just think philosophically, I'd be interested in your thoughts on that.
Yeah, no, I agree that there are different interpretation of what do we mean by neutral, because like we could think truly species do not interact. That is kind of a difficult philosophical view to keep, like, because we see like lions eating gazelles. They definitely are interacting. At least if you ask the gazelle, you will get a yes for sure. But also, like, we could have maybe like competitors, and to some extent, they sorted themselves such that they have very, very weak interactions, right? Like, because they try to partition their resources, or in fact, like, they could have basically no interaction whatsoever. So in this case, it's not that like they would not have had interactions to begin with. It's just that after like all these pieces are sorted, we don't really have interactions. Or another interpretation is like these interactions don't really matter, like are much smaller than other processes that dominate the dynamics, right? Like all of these are philosophically like a slightly different interpretation of the same phenomenon.
Right. I mean, they may matter a lot at fine scales, but when you coarse grain, they may average out sort of due to law of large numbers.
Yeah. In fact, like going back on that, one thing that I like a lot is what if we now, instead of having no interaction, we have random interactions?
Yeah.
Then we assemble systems like that. What you find is that like the statistics look very much like the neutral model, even though it's basically the opposite of a neutral model, in which like species have much, much stronger interactions, but still like a lot of the results that you would derive look about the same.
Right.
Yeah.
And the other point, right, the other technical point, maybe it's not necessary that I put in the chat, is that you might have a stable limit cycle, and the equilibrium point inside is not necessarily unstable. It might be stable with, let's say in 2 dimensions, there's some unstable limit cycle that separates them, and in higher dimensions, some more complicated behaviors that could go on. I don't know to what extent, maybe you can comment, that's possible in the Lotka-Volterra equation.
Like Lotka-Volterra, that would not be possible, right? Like, because we have like this much, much simpler model like for dynamics. But yeah, in generic model, we could have much more complicated like dynamics, such that a certain area goes to some equilibrium, some other area goes to a limit cycle, or an unstable limit cycle shuffles like the system between two different...
All sorts of things, yeah.
Yeah, it gets really interesting and really complicated. That's why I wanted to do Lotka-Volterra, because it's just like the simplest that you can think of.
Anyway, brilliant overview. Thank you.
Thank you.
Great, thanks a lot. Any other comment or question?
All right, and if you don't have any other, like, you can ask them like the next lecture, or you can go over the notes again, and then maybe some questions will arise. And feel free like to even email me, and I'll answer them before I start next time.
Exactly. So Stefano will give the second lecture of 3 this Friday, so you have time to think about. There is a question actually in the chat. So how does a constraint on the total population, as seen in the replicator equation, change the stability criterion for a fixed point? In other words, does the community matrix for a LV system with and without this constraint have the same stability criterion?
That's a very interesting question. It's too bad that I'm not talking a lot. I love the replicator equation, and I have other lectures on the replicator equation. So the question is, what if we put some other constraints? For example, in the replicator equation is basically the cousin of Lotka-Volterra. The only difference is that now we're tracking proportions of the density of species rather than the densities themselves, right? So imagine that these proportions always sum to 1, which means that if one species has to go up, somebody else has to go down, because they have to sum to the same number. In the replicator equation, when you're doing this sort of linearization around an equilibrium point, you will always find a direction that is the direction orthogonal to the simplex, right? Like you have a direction in which, instead of like staying such that the proportions sum to 1, now all the proportions sum to some larger number or smaller number, right? That direction that is orthogonal to the simplex, you can discard, because you don't really care. You know that the dynamics keeps the system in the simplex, and as such, this direction, this extra direction, you don't care. In fact, like I would suggest, like maybe I'll put like some sort of like link in the chat. There is a beautiful equivalence between replicator equation and Lotka-Volterra. So for every Lotka-Volterra, you can write a replicator equation with one more species, where species is not a real species anymore. And conversely, for every replicator equation, you can write a Lotka-Volterra system by ditching one of the species.
Great. So, well, I think if there are other questions, you can ask Stefano on Friday. So thanks again, Stefano, for giving this lecture and everybody to participate. And we'll see each other again tomorrow at the usual time at 1:15 Italian time for the first lecture by Marino Gatto. So thank you very much and see you tomorrow.